Hello everyone. Today we are going to start with organic chemistry. Why organic chemistry is so special? Because it is made up of only few elements. Entire organic chemistry you can fill it with carbon, nitrogen, hydrogen, oxygen, sulfur. Using these five elements you can cover up to most of the organic chemistry compounds. Organic compounds, right? Out of this, the most interesting and our hero, that is carbon. We'll talk about carbon in a while. Before that, I would like to tell you about organic chemistry. What is that? What are organic compounds? So first, about 200 years ago, people were thinking that organic compounds are the one which is from.
Hello everyone. Today we are going to start with organic chemistry. Why organic chemistry is so special? Because it is made up of only few elements. Entire organic chemistry you can fill it with carbon, nitrogen, hydrogen, oxygen, sulfur. Using these five elements you can cover up to most of the organic chemistry compounds. Organic compounds, right? Out of this, the most interesting and our hero, that is carbon. We'll talk about carbon in a while. Before that, I would like to tell you about organic chemistry. What is that? What are organic compounds?
Hello everyone. Today we are going to start with organic chemistry. Why organic chemistry is so special? Because it is made up of only few elements. Entire organic chemistry you can fill it with carbon, nitrogen, hydrogen, oxygen, sulfur. Using these five elements you can cover up to most of the organic chemistry compounds. Organic compounds, right? Out of this, the most interesting and our hero, that is carbon. We'll talk about carbon in a while. Before that, I would like to tell you about organic chemistry. What is that? What are organic compounds? So first, about 200 years ago, people were thinking that organic compounds are the one which is from animals and plants. In case of inorganic compounds, they are from mineral sources. People were thinking like that. But there was a chemist called F. Olher. In the year of 1828, he synthesized the first organic compound. Have you ever wondered, we are having so many compounds in our textbook, our reference books. What would be the first organic compound ever synthesized? That is none other than urea. F. Olher synthesized urea from an inorganic compound, that is ammonium cyanate. The formula of urea is NH2CONH2. This is the first ever synthesized organic compounds. Okay, after that they started working upon with methane, acetic acid, and etc. Okay, but why carbon is so special? Why carbon is having a property to form an entire branch in chemistry? For that, I would like to tell you the important property of carbon, that is catenation. In the entire periodic table, out of other elements, carbon is having this catenation property. What is this, ma'am? This is the tendency of self-linkage. What is that? Tendency of self-linkage means carbon can bind up to another carbon, and another carbon, and so on. It can extend to form long chains and rings. Carbon shows maximum catenation property out of other elements in the periodic table. It can combine with other atom also, or carbon can combine with another carbon through single bond, double bond and triple bond. Okay. Any other element is having that property? Yes. The next two carbons, silicon, I'm talking about in row wise. So silicon, atomic number 14, that is also having the catenation property, but not as good as carbon. It is very short, but carbon can form in number of bondages with other carbon. Okay, that makes carbon so special. Each one of the elements should have some identity, right? Okay, you say carbon can form bonds with other carbon, but how many bonds it can form? One carbon can form how many bonds? Carbon can form 4 bonds. How? How the valency of carbon becomes tetravalence? What is tetravalency? The valency of carbon is 4. How that happens? What about other elements? Let's see. For that, we must know about the electronic configuration of carbon. That is 1s2, 2s2, 2p6. 2p2. Correct. If you are not aware of how to write these electronic configurations, please let me know in the comments. We will create a short trick video for this. Okay. Coming back to the topic. Here I have 2 in the first shell, 4 in the second shell, that is the outermost shell. So let's draw these electrons. 1s, 2s and 2p2. Okay, so this is the ground state configuration of carbon. What is this ground state, ma'am? Ground state is like the normal state without any disturbances, without any interference of other atoms towards the carbon. But what happens if some other nuclei is approaching carbon? Before that, tell me, what will you do if your friends or the guest or your relatives are coming to your house for staying? You will do the accommodation. You will make up the bed, create some space for their stay, right? Similarly, the atoms also behave like that under one condition. Each room, these boxes should contain carbon electron also, then another electron of other atom can form and share that space, right? For example, let's say another carbon, or let's say hydrogen, the simplest atom, right? Hydrogen is coming towards carbon atom. Okay, so carbon will get excited state. So in that case, what will happen? 1s, that is the inner shell, that remains intact. What about 2s and 2p? The one electron of 2s will get excited to 2p, so that now the configuration becomes 2s is having 1 and 2p is having 3. If I want to fill up these spaces, how many electrons it need to reach the stability, or how many electrons it need to become a neon gas configuration? It requires 4 electrons. So those 4 electrons will be given by the incoming atom. The sharing will happen. So remember, entire organic chemistry or most of the organic compounds is made up of covalent bonding. What is covalent bonding? It is a sharing of electrons. Each bond will consist of 2 electrons, one from one atom, another electron from another atom. That's quite a sharing. Okay. So that makes carbon is having tetravalency. What about oxygen? What about nitrogen? What about sulfur? What about hydrogen? Okay, you can work on those elements. Now I'm going to give you the numbers only. For example, hydrogen, the valency is 1, oxygen 2. What I mentioned valency here, that is, it can form up to that many bonds. Not up to, like, it should form that many bonds to be neutral, to remain as neutral. So nitrogen 3. Okay, you can remember it like HONC, which stands for 1, 2, 3 and 4. Honk. Hydrocarbon, by the name indicates, that is having only carbon and hydrogens. So most important hydrocarbons are actually 4. First I like to tell you the first 3, that is alkanes, alkenes and alkynes. What are these? What is the difference of these 3 hydrocarbons? The first one, which is saturated one, other 2 are unsaturated. That is the major difference. What is saturated and what is unsaturated? In the oil packets, in the advertisement of oils or some other food elements, you can see saturated fatty acids or unsaturated fatty acids. Right? What are that? What is that? We'll see. First of all, let's understand what are these 3 categories: alkanes and alkenes and alkynes. These are having the general formula of 2n H2n plus 2. For example, if I am giving n is equal to 1, then the formula becomes C1 H 2 into 1 2 plus 2 4. So CH of 4 it becomes. If n is equal to 2, then it is C2 H6 and so on. You can substitute it up to any number. Similarly, in case of alkenes, it is having CnH2n, where n is equal to 1, 2, 3, 4 and etc. Then the first, if I am substituting 1, what will happen? If I am substituting 1 in case of alkenes, what will happen? C1H2. But that is not possible. Carbon should have 4 bonds, right? So this is not possible. It should start with 2 carbon system. So C2H4, that is the first alkene. For alkynes, the formula is CnH2n H2N minus 2, where the N starts from 2. So it becomes C2H2. Okay, so here you can see the number of hydrogens are getting decreased. So what will happen to the bonds? In case of alkanes, it will have only single bond or only sigma bonds. But in case of alkenes, it can have single and double bonds, pi bonds as well, right? Double bonds or pi bonds. The single and double bonds are allowed. In case of alkynes, single and triple bond. Okay, so these are the main differences between these three. We'll see about these alkanes, alkenes and alkynes in the upcoming video in detail, how to prepare it, what are the bonds involved there and what else it can do. We'll see there. Now let's move on to how we can write the organic compounds. What are the ways to write the organic compounds? Okay, so now the representation. First, I can write it through molecular formula like IZCH4, C2H6 or C2H2. Okay, so those are molecular formulas. And second thing is structural formula. Structural formula can be classified into two, that is expanded one and condensed one. For example, expanded one for methane is, that is CH4 is, I just have to write each of those bonds, right? In case of condensed, let's say I'm taking 2 carbon system, that works better. So in that case, I have to write it as CH3, CH3. If I want to write the expanded form of C2H6, then I should write it as again one CH3 with expanded one. Okay. Other than this, we have another representation, that is bond line. Bond line formula. What is that? Here you can see, would like to take that for 3 carbon system. For example, if I'm having C3 of alkane, so which makes it H8. So 1, 2, 3. So this is the bond line formula of C3H8, which represents each of these corners are having carbon and remaining hydrogen parts are understood. Hydrogens will not be represented here, but you have to understand that. Like you can see the first one. Let me do that in different color. So the pink one is 1 carbon and blue one is in another carbon. Green one is another carbon. Okay. In that case, The pink one is attached with blue carbon. So remaining 3 bonds are left. So those will be hydrogen. Okay, so this is CH3. And blue one. Blue one is having 2 bonds with pink and green. So remaining 2 hydrogens must be there. That is CH2. The same thing for green one as pink. It becomes CH3. Okay. So this form, I just written it here as bond line formula. I'm sure if that is confusing for now, but end of this organic chemistry series, you will be master in writing these formulas and reactions, mechanisms and everything. Okay. So don't get scared. We'll go step by step with detailed explanation. So if you have any doubts at any time, please tell me in the comments. Okay. Of organic compounds. Major classifications. This is broadly classified into acyclic and cyclic. Acyclic is further classified into straight chain and branched chain. Cyclic is classified into aromatic and alicyclic. Okay, so what are these? By the name represents, acyclic is not having any closed system like a ring. It can be starting from 3 carbon system. Okay, like this. So it should have, cyclic means it should have a closed system of carbons. Acyclic means there is no closed system, there is no rings. But in case of cyclic, that will have the closed system. Okay. So acyclic straight chains. Then it will have the representation like this without any interfering of other carbons. But in case of branched, you can see some other groups will get attached over here. Okay, these are branches. It is branched chain of acyclic. What about cyclic? In cyclic, we have aromatic and alicyclic. Aromatic are the one which can be classified into 3. One is benzenoid. The cyclic structure which is made up of only benzenes, or non-benzenoids, and finally heterocyclic. So benzene will have carbons only, carbon and hydrogens. Non-benzenoid, that is not having the benzene structure. But in the case of heterocyclic, it will have other atoms as well. It can have nitrogen, it can have sulfur, for example thiophene, for example pyridine. They are aromatic heterocyclic compound. Similarly, alicyclic will have 2 classifications, that is homocyclic and heterocyclic. Homo means same atom will be there. Hetero means different atoms will be there. Okay. Hello everyone. Today we are going to see the crash course of hydrocarbon. Today we are going to discuss haloalkanes and halogens. Alkyl halides and aryl halides. We are going to cover this chapter in 2 parts. Which chapter includes preparation of alkanes of haloalkanes, and we are going to understand the nature of CH bond, followed by how it is behaving, how it can be produced, and that where the stable intermediate can be formed. Okay, so intermediate must be longer lived when compared to the other intermediate formation. What is that, ma'am? What are you referring to intermediate? I'll tell you an example. For example, if I am taking CH3, CH double bond CH2 reacting with HCl. Okay, so what are the intermediates it can form? First, it can undergo slow step, which is the rate determining step, to give an intermediate like this. So the double bond breakage will happen and CH bond CH2 and H plus will get joined to this carbon. This can be one of those intermediate, which is a secondary carbocation. What about another intermediate formation? In this case, H plus will join on the secondary carbon. CH3, CH and CH2 plus. Here the carbocation is primary. So tell me, which is more stable carbocation, primary or secondary? Of course, secondary carbocation is more stable compared to primary. Why is it so? We are going to cover that in today's session. Okay, after that what will happen? After that the Cl minus will get attached to the most stable intermediate to give the product as CH3, CHCl, CH3. So that would be our major product, which is 2-chloropropane. If the reaction goes via less stable intermediate formation, then the product is CH3, CH2, CH2, Cl, which is 1-chloropropane. That is a minor product. So hope you got an idea what is intermediate. So how the intermediate affect the product formation. Okay, so is there any types of intermediate? Yes, it has some types. Before that, I would like to introduce how the reaction happens, how the bond fission happens. Like in the first example, I showed you the double bond is breaking, and the HCl, the bond between hydrogen and fluorine, which is also getting separated. So the bond breaking will happen over there. How that happens? What are the types of bond fission? Fission means separation, right? So what are the types of bond fission? It can be of homolytic fission and heterolytic fission. As I told you, homo means same, hetero means different. So first let's talk about homolytic fission. Homo, which is same, lytic means separation. So if I am having a molecule of A2, that can be referred as A bond A. So in case of homolytic fission, the bond, the A of A placed in the corners of the bond will get one electron each. For example, the one electron will go to 1A and another electron in the bond goes to another A. So as a result, 2A is having 1 electron each out of the separation. Okay, so this is called homolytic fission. And what is this intermediate is called? This intermediate is called free radical, where it has unpaired electron. Okay, so this is having only one electron, which refers to as chargeless, and since it is having one electron, that is a paramagnetic species. Also called as odd electron species. Any example we encountered in our reactions? Yes. I'll give you an example of Cl2, which can be written as Cl bond Cl. Each one of those electrons will be taken by Cl. So you have to remember one thing, only one electron is going to one atom. So I have to refer this as this kind of arrow. It's not a double-headed one, it should be a fish hook arrow. This is called fish hook arrow. Okay, so as a result of this, I will be getting 2Cl radical. Mostly the reaction happens in the presence of sunlight or UV will happen like the radical formation, free radical formation. Okay, one more example I will give you for carbon free radical. That is, if a carbon is breaking like this, I'm having a Cl radical. So if the breaking happens like this, then it will lead to the formation of carbon free radical plus HCl. Because each one of those hydrogen free radical and Cl free radical is combined to form HCl. Okay, so this is carbon free radical. Okay, so these species which the carbon is having an odd electron, please remember, and this is paramagnetic, that is not having any charges. What about the hybridization of these compounds? What about the hybridization of this carbon free radical? As you can see here, that will have 7 electrons total, right? Already carbon is having 6. The 1 electron from the bond, so it will be a 7 electron. So which will be look like carbon. Let's say these bonds are filled with the substituent. You can take any substituent or hydrogen also. Remaining 1 electron will occupy one of those orbitals. Okay, so in this case, what would be the hybridization? So the hybridization of this carbon will be sp3 but trigonal pyramidal shape. Okay, so you can take CF3, you can take CH3 radical, and one more thing you have to remember, these are electron deficient compound. These are electron deficient compound because that lacks of 1 electron. Okay, so what about the intermediate stability? which intermediate would be more stable? If I'm comparing it with CH3 or of all three sides and one radical, and if I'm comparing it with secondary carbon, and if I'm having primary carbon, out of these three, which is more stable? Of course, the tertiary one is more stable when we are compared to secondary, and then comes primary. Why is it so? We'll see in a while. You will understand in a while automatically. Okay, the next type of cleavage or fission, which is heterolytic fission. So heterolytic fission means it's not same, it's different, is it? So if I'm taking A, B, that is giving A plus and B minus. So what it indicates? Both the electrons are taken by B, and A becomes positively charged, which lacks of electron, which lacks of negative charge, right? So heterolytic fission leads to the formation of ions. For example, you can take C with Cl, okay, which will give you carbocation and Cl minus. So the electron will get shifted to Cl. Okay, so these are called carbocation. Cation means positively charged, we know. That here the carbon is positively charged, so this is carbocation. Okay, so what is the property of these carbocations? Of course, these are positively charged species. These are one of those intermediates. Positively charged. And what about the hybridization? This is sp2 trigonal planar. So where it is having an empty p orbital, right? And most importantly, these are electrophiles. Ma'am, what is electrophile? These are electron deficient or electron loving species. Which will be ready to accept the electrons. Any other examples you see in a normal reaction? Here you can see BF3, which is also having a trigonal planar structure, and that is having a empty orbital in it. Similarly, you can try it out with AlCl3, or you can try it out with C+. Correct. So these are some Lewis acids you can take, which is ready to accept the electrons. These are some electrophiles example, and which are electron deficient also. Okay. Then let's move on to magnetic property, whether that is paramagnetic or diamagnetic. Of course, that is a diamagnetic species because there is no unpaired electrons like we saw in free radicals. These are diamagnetic. And what about the minus charged species or negatively charged species? How it can be formed? You said carbon will get positive charge and Cl will get negative charge. Carbon can also be negative. Yes, it can. For example, here if I am taking with MgX, where Mg will be more positive, that is a metal. So it creates C minus plus Mgx bearing a positive charge. Okay, so this is called carboanion. Okay, let's list down the properties of carboanion. Negatively charged, whether it will be paramagnetic or diamagnetic. It's diamagnetic, of course. It is not having any unpaired electrons, and this is an electron-rich substance or electron-rich species, which is also called as nucleophiles. It's just opposite to electrophile, which are hating electrons. Any other examples for carboanions? Yes, we have. It can be of any species which are bearing minus charged. Here you can see carbon is having minus charge, that is a tertiary carbon. Similarly, you can write down for secondary carbon and primary carbons as well, and methyl as well, methyl carboanion. More importantly, you will see this type of structure, CH2 double bond CH, CH2 minus, which is called as allylic carbocation. Sorry, carboanion. Allylic carbon is the double bond, the next to double bond bearing carbon. So what about the carbon which is having the double bond? For example, like this. Then that is vinylic carboanion. This is vinylic carbon. And you have to understand one more, that is benzylic carbon. For example, the carbon attached with the benzene ring. You should not take this carbon as a negatively charged while reacting with this kind of benzylic carbon. You please be careful. This is benzylic carbon, the carbon attached with the benzene ring, not in the carbon in the benzene ring. Okay, so these are the only intermediates? No, there is one more, that is carbenes. What is that? So carbenes are the one, for example, if I am taking a structure like this, I am treating it with alcoholic KOH, let's say KH plus and OH minus. So what will happen? Obviously H plus will be created by donating all those electrons to carbon, right? Similarly, chlorine will take up both the electrons from the bond and leaving those bonds. So this will create a empty space, empty orbital over here, and this will create a 2 carbon over there on the carbon, 2 electrons on the carbon. Remaining the product, or KCl and H2O will be formed. Okay. This kind of carbon is called carbenes. Okay, where those electrons will reside? We have 2 electrons in the carbon, so where that will be occupied? So carbenes which are bearing two electrons, lone pair electrons, that can be of two types. One is singlet carbene, where the electrons are in the same orbital. This is empty orbital produced in the above reaction, and both the electrons are in the same orbital, that is called singlet carbene. And if an electron is on the different orbital, then that is triplet. Then that is triplet carbene. Okay, so how the name comes, it's not so important over here, that is depend on the spin multiplicity. But you can remember, this is if both the electrons are in the same orbital, then that is singlet. Both the electrons are the different orbitals, you can remember that as a triplet. Okay, so out of these two, which is more stable, singlet or triplet? So for that we have to understand their properties. The first one, singlet, which will have sp2 hybridization. In case of triplet, it will have sp hybridization and linear. So if sp2 means that will be bent structure like water. This is linear, and you know about magnetic property. The singlet one or diamagnetic, and the triplet one is paramagnetic. Okay, so among these two, which is more stable? While talking about the stability of singlet and triplet, you can clearly see that in case of singlet, that will experience more of repulsions, electron-electron repulsion, which makes it less stable than the triplet one, which is not facing any issues. Okay, but there is one exceptional cases where it comes the formation of back bonding. What is that back bonding? We know that singlet will have an empty orbital in it, like this, which will have an empty orbital. So what will happen if one of those places, if I am having Cl, if I am having any electron rich species which will be able to donate its lone pair. So in that case, this can accept that electrons, this empty orbital can accept this electron to form back bonding. So if more bonding means what will happen? More strong. It will have more stability. That kind of stability will not happen in case of triplet, even that is having Cl. So which makes it more stable for singlet due to back bonding. If there is a back bonding possibility, then singlet is more stable than the triplet. So back bonding is nothing but p-pi bonding. Okay, so now it's time to focus on more of displacement effects. So if you heard this much, take a break for 5 minutes and come back with full potential. Let's focus more on electronic displacement effects. What is that? Why that is so important to understand this in covalent bonding? Because this determines the stability. Because whatever the reactions happening in the world, its final destination, final place Why that is happening? The reason is that stability. So these four effects. The first one is inductive effect. Second one, mesomeric effect, or also called resonance effect. Third one, that is hyperconjugation, also known as Baker-Norton effect. And the fourth one, that is electromeric effect. We have to understand these four to know their stabilities of carbocation, carboanion, free radicals, carbenes, and etc. Okay, now let's start with the inductive effect. What is that? So inductive effect is nothing but it is a permanent effect. What happens over here? Permanent displacement of sigma electrons. That is more important. Sigma electrons along the, of course, the saturated carbon chain towards more electronegative atom. Of course, it will go to more electronegative atom because electronegative means which directly refers to the attraction of electrons towards itself. You can see in the carbocation formation, in the particularly the heterolytic cleavage, heterolytic fission, where if there is more of electron negativity difference, then it will undergo heterolytic fission. If the electronegativity is less or same, for example Cl2, that will undergo homolytic fission. If I am taking HCl, that will have more electronegativity changes, differences. So it will undergo heterolytic fission, right? So here we are talking about permanent displacement of sigma electron towards the electronegative atom. What is that? Let me take a carbon which is attached with the electronegative atom, that is halogen, let's say. So what will happen? This is having a more electrons, electronegativity, so which will pull the carbon electrons also, because this is electronegative. Due to that, the negative charge, slightly more negative charge is produced on this electronegative atom due to pulling of electrons and giving up of electrons. It's not entirely giving up, but the electrons are moving towards halogens or any electronegative atom, so that here slight positive charge is produced. Okay, so which will lead to the polar covalent bond. Which will lead to polar covalent bond. What is polarity? Difference in charges, is it? So which will lead to polar covalent bond. Due to the more electronegativity of an atom, it is just pulling those electrons. Due to that, the slight positive and negative charges created on the respective atom. That is called inductive effect. Okay, so this is having a two types: positive inductive effect and negative inductive effect. So where positive inductive effect happens? This happens where the electron releasing groups are there. Electron releasing groups are also called as electron repelling group. You can take anything. For example, all alkyl groups, which always wanted to be in positive charged, so which will give up, which will ready to give up the electrons. So all alkyl groups are undergoing plus I effect. You know, I told you why tertiary carbocation is more stable than the secondary, then comes primary and then methyl. Because tertiary is having more positive inductive effect. It's just giving up the electrons to positively charged carbon to neutralize the compound, so that will be more stable. And if I'm comparing it with secondary, what will happen? That is having only 2 methyl groups. And for primary, that will have only 1 methyl group. So that's why tertiary is more stable than the secondary, then comes primary. Is it clear? This is super important. Whenever you are doing any reactions, this is much more important. Okay, so what about minus inductive effect, minus I effect? It's just opposite to plus. Where will happen? Electron withdrawing groups are there, means electron withdrawing groups. For example, halogens. Any group or an atom which is having more electron attracting power than the hydrogen, there this effect can have. More electron withdrawing than hydrogen, this effect will happen. You can take halogens, you can take nitro, cyano, even alkynes, alkenes. Okay, so these will undergo minus I effect. I can give you the order also. For example, nitro, which will give you more electron withdrawing effect, and then comes cyano, then keto group, then comes our halogens F, Cl, Br, iodine, OH, don't get confused with other effects. In case of plus inductive effect, only alkyl groups. Remember it like that. Only alkyl groups. In case of minus I effect, you can take these groups. Mostly your exams will get covered with these groups. Okay, ma'am, why are you dragging these alkynes and alkanes over here? Of course, these are also having more electronegativity, because this is sp hybridized with 50% s character, and this is sp2 hybridized, where it is having 33.3% of s character. More the s character, more will be electronegativity and more acidity, isn't it? Okay, are we clear about minus I effect? So, why we need to understand minus I effect? What is the application of minus I effect? I'll give you shortly. The first thing, stability of carbocation. I told you. It's depend on plus I effect. Okay. Then the second application is stability of carboanions. Carboanions which is negatively charged. So negatively charged, if that is having electron withdrawing, means that will get neutralized. So that becomes more stable than the electron releasing group presence. Right? For example, if I am taking CH2 minus with is attached with NO2. Okay, that becomes much more stable because NO2 is taking up the electron, trying to take up the electron, so that the negative charge become balanced, so which becomes more stable. Then comes methyl, and then comes if an electron releasing group is attached, like for example CH3 CH2 minus. So in that case already that is electron rich, negative charge is having, this is also giving the electron, means the stability will get decreased. Okay, but here you have to consider one thing. If I am taking CF3 minus and CCl3 minus, then CH3 minus. Okay, so what will happen? We discussed it earlier. In this case, this guy is having negative charge and 3 fluorines attached to it, fluorides, so which will take up the electrons. Okay, what about CCl3? Once again it will have and CCl3, it will try to take up the electrons. In that case, what can happen? Cl, particularly Cl, is having a empty 3d orbital. Empty 3d orbital, isn't it? So Cl configuration, which will have empty 3d orbital, so that these electrons will form a bond which is called p-pi d-pi bond. Which makes it much more stable. Then in case of CH3, we very well know about that. There is nothing to talk much about CH3 carbanion. So which is more stable? What would be the stability order? If I am talking about the stability, CCl3 is more stable than other two. And then comes CF3 and then CH3. Okay. Then the third application is basic strength of amines. So amines which will have NH2 groups. Amines that is having a lone pair in it, the nitrogen. So this is also called as Lewis base, which is also called as nitrogen is willing to donate the electrons. So if the ease of donation is increases, then what will happen? The basic strength will increase. So comparing primary, secondary and tertiary amine. Tertiary amines becomes more basic, then comes secondary, then comes primary, then ammonia. Because already nitrogen is willing to donate, CH3 groups, alkyl groups attached to the nitrogen will make it much more easier. So increase of ease of donation means increase in basicity. Okay, so the next application, that is acidic strength of carboxylic acid. So carboxylic acid that will have COOH group. As the name indicates, that is more acidic. So what will happen to carboxylic acid? Because of this inductive effect, OH is there. So which will form the conjugate base of C double bond O, O minus, right? Because H plus will be leaving, so O is more electron withdrawing, more electronegative. It is forming a conjugate base. So the conjugate base is more stable, the acidity is increases. Conjugate base stability is directly proportional to acidity. Right. So the next effect we are going to talk about is resonance or mesomeric effect. This is very simple effect and a very important effect to be remembered. It is resonance effect. Where we heard about the term resonance? While we are talking about aromaticity, benzenes, we talked about it, right? So which is nothing but delocalization of pi electrons. Delocalization of pi electrons in conjugated systems. Conjugation means alternate double bonds, double and single bonds, right? So in delocalization of pi electrons in conjugated system is called mesomeric effect. For example, you can take how the delocalization happens. So the first double bond will give up the electrons to the next carbon. So this becomes positive. I'm writing it here. So this becomes positive and CH that becomes negative. Then comes this negative, which is combined with the positive created by this carbon, so which forms the bond. Then you have to proceed with CH2 with the positive charge. So here there is no negative which involved in the bond formation. Okay, I could delete it. Please forget this. So this is what the delocalization happens. So what is the importance of this? So remember one thing. If you are having more weight on your hand, how many hours will you able to sustain with that weight? Let's say 2 hours. If you are having your friend beside you and you are changing the hands of your weight, how many hours you can sustain with you two with the weight? More than 2 hours, right? The similar thing happens over here. The delocalization increases the stability. This is also categorized as plus M effect and minus M effect. Plus M effect groups are where it can happen is wherever the electron donating groups are there. Electron donating means electron releasing. Wherever the electron donating groups are there. For example, OR, OH. Ma'am, you told OH is in minus I effect. Yes, I do. That's why I told you don't get confused. OH, which is having a oxygen that is negatively charged, electronegative, that's why it is giving you the minus I effect. Here we are talking about electron donating groups. So where NH2 comes and NHR, where it is having the lone pairs. Here also oxygen is having the lone pair which can donate. And what else? Halogens, of course. So the halogens which can donate the electrons. Here what can happen? For example, if I am taking CH2 double bond CHCl. So Cl is having a lone pair which will be given up to the bond formation. So can form CH double bond Cl with the positive charge, and what happens to this carbon, the first carbon, that becomes negative with a single bond. Okay, so this kind of delocalization can happen. You can consider the best delocalization example with the benzenes. Okay, so here the question can be asked, compare the bond strength. You can consider CH3, CH2Cl and CH2 double bond CHCl. Comparing A and B, which is having more bond strength in case of CCl? Which is having more bond strength in case of CCl? A or B? So let me know in the comments below, A or B. If you don't know the answer also, let me know. We'll discuss it in shorts. Okay. I told you which is the best example in case of benzene, is it? So let me take this phenol. Okay, so what can happen? Oxygen is having the lone pair, so it is donating to this carbon. So the negative charge goes over here. The bond is taking up the positive part, so which creates a negative charge on this carbon and double bond over here, and oxygen becomes positive. Remaining bonds remain same. Then again this negative charge goes here, so that this position, para position, becomes negatively charged. Guys, this is very, very important. You can see this delocalization in hydrocarbons chapter as well, where how the electrophile directing happens in case of substituent presence, right? So please be careful, please be mindful while you are drawing this. So the negative charge produced over here, the double bond comes here, oxygen with the positive charge, then Once again, double bond, double bond, double bond O with the positive with hydrogen and a negative charge go to another ortho position, which makes it again the benzene structure with varying double and single bonds, right? So here you can see ortho and para positions are electron rich. So you can say if electron releasing group is present over there means ortho and para positions becomes electron rich, which triggers the electrophile to come and attack over there. Okay, so what about minus I effect, ma'am? Minus M effect, ma'am? It's just opposite to that. Electron withdrawing groups are present. For example, nitro, CO, cyanide, and much more. I will be attaching the list of electron withdrawing and electron donating groups over there. You can draw a benzene structure with an electron withdrawing group, that is, let's say nitro. So where it has the nitrogen that is having a, either you can mention it in the coordinate bond, I'm just mentioning it with charge. So it is taking up the electron. Due to that, what will happen? This part becomes positive, right? It is taking up the electron, so this part becomes positive. So double bond, oxygen with the negative charge, and remaining stays same. Again, you can consider, again it will pull up the electrons, so the double bond will be placed over here and the positive charge goes to para position. Once again the resonance happens, another ortho position becomes negative and finally becomes positive, and here comes the double bond O. Again nitrobenzene is formed. You can see, comparing ortho, para and meta positions, meta is electron rich. If electron withdrawing group is present in the benzene ring, and ortho and para becomes electron deficient. Okay, this is point to be noted, please note it down. This will be very helpful in case of substitution reactions. We already discussed about the stability, which will give you more stability, more the resonance, more stability. And in case of carboanions, plus M effect decreases the stability, and if there is a minus M effect, it increases the stability. And resonance in phenol, we already discussed about that, and how the electron rich and electron deficient positions are created. The next effect we are going to talk, that is hyperconjugation. So hyperconjugation, this delocalization of, sorry for this spelling mistake, it's delocalization of sigma electrons, again sigma electrons, which is also called as no bond resonance. There is no bond, yes, there is no bond formation. It's like bond will disappear. Like for example, you can see the first type, that is sigma to PMT, where it happens like if I'm taking CH3, attached with an carbocation that will have a empty orbital, is it? So that empty orbital, that is a sp2 hybridized carbon, the electron shift happens to, this is sp2 carbon. Okay, so the bond breaking happens over here. H plus is going or sitting there like this, and due to that what will happen, it will become electron rich. So those electrons are given to this empty orbital so that the double bond will be formed. So which makes this more stabilized. That is, happens for each of these, any of these hydrogen can go, right? So how many hyperconjugative structures can be written for this? There are 3 hyperconjugative structures for each one of these hydrogens. So total 3 hyperconjugative structures. So why the hyperconjugative structures are important? How we can determine how many hyperconjugative structures can be written? So the number of beta hydrogens is equal to or proportional to, you can take the hyperconjugative structures. More the number of hyperconjugative structure, more will be stability. Okay, so for example, if I am talking about tertiary, that will have tertiary carbocation, then that will have 9 beta hydrogens, correct? So which will have more stable than secondary, which that is having 6 beta hydrogens, and then comes primary, that is having 3 beta hydrogens. Then finally methyl carbocation, that is not at all having any hydrogens, so which makes it least stable. The most stable one is tertiary carbocation with high number of hyperconjugative structures. Okay, so let's move on to alkenes. So what happens to alkenes in case of hyperconjugation? Here you can see, let me take CH3 in one of those substituent. So what will happen? This hydrogen will goes away, the carbon gets the negative charge. So that negative charge will get shifted to this carbon, correct? So due to that, what can happen? The shift, so that the formation will be C with H plus, other 2 hydrogens will be there, then double bond will be formed in this carbon, and the single bond will be there in this with the negative charge. Similarly, you can form the structures with other 2 hydrogens as well. So if you are having CH3 in all 4 positions, then you can have more number of hyperconjugative structures. Okay, it's more related to the resonance, but it happens in case of sigma electrons, but the resonance happens in pi electrons. Okay, then the last effect we are going to see, that is a very simplest effect known as electromeric effect. Among these 4, this effect is very simple effect. Also, this is called temporary displacement. Why this is temporary? Because it is dependent on the incoming group. For example, if I'm having the alkene system, okay, so I'm having alkene system, the incoming group is Cn minus, it's considered. So the Cn minus makes it, it will break the double bond. It's a H plus and Cn minus. So H plus will get attached to the one of those carbons, and Cn minus will get attached to the another carbon, right? So due to the H plus presence, so what will happen? The attraction between one carbon to the H plus, correct? So in that case, bond breakage will happen. So this becomes slightly positive, negative, and this becomes slightly positive. So the bond breakage, here comes C with the H plus attached to the CH, and this carbon becomes positive, and followed by Cn attack, so that Cn and HCN will get attached. So what if instead of H plus, this Cn is starting over the reaction? Then one of those carbons will get negative charge. So that's carbocation formation, carboanion formation, that discussed about the electromeric effect. Okay, so in today's session we have discussed more about the effects and the intermediate formation. In next session we'll discuss detailedly about aromaticity. So don't miss out the next session, because you can expect at least a question from aromaticity concept. Okay, so please do more practice questions. I'll be attaching some practice questions in the description below. Please do that. Thank you. We are going to talk about substitution reaction. What is substitution? Substitution is nothing but the replacement. More technically, if I want to speak, then the substitution reaction is in which the functional group of one chemical compound is getting substituted by the another group or replaced by the another atom. Those are called the substitution reactions. Say for example, if I am having ROH, I am using HX. As the end product, I am getting RX plus H2. What happened over here? OH is replaced by RX. So that is substitution reaction. Here we have two types of substitution reactions. One is electrophilic substitution reaction and the second one is nucleophilic substitution reaction. Electrophile, nucleophile. What is the difference? Electrophiles are the one which are electron loving species and the nucleophiles are electron hating species. Out of these two, today we are going to see in detail about nucleophilic substitution reaction. Why only that? Because electrophilic substitution reaction we are going to see that in haloalkanes chapter in detail. Now let's see about nucleophilic substitution reaction. What is nucleophile? Electron loving species. Okay, so how we can identify that? How it will be present? By seeing any molecule or an atom, how I'll get to conclude that is a nucleophile. Yes, you can do that. Because nucleophiles are the one are ready to share its electrons. They are electron hating. Correct? So usually that will have unshared electron pairs. For example, ammonia, which is having a lone pair in it. Correct? So Lewis bases or the nucleophiles. Any other nucleophile we are encountering in reaction mechanism? Yes. The nucleophiles are there of three types. The first type is negatively charged. Of course it would be negatively charged because they are electron rich. So for example, you can take OH minus, Cl minus. These are some famous nucleophiles. Of course are halo groups Cl minus, F minus, I minus, Br minus and etc. Apart from that, we have NO3 minus, SH, thio group SH minus, or RCOO minus, OR minus, sometimes H minus, hydrate as well. We will see more reactions about that. And the second type is that all Lewis bases, which are containing one lone pairs. For example, RMGX, RLI, or lithium aluminum hydride, R2ZN, or organometallic compounds are considered Lewis bases of nucleophile. How ma'am, how these are having electrons to be donated, how it can act as a nucleophile? Yes, you can see, I told you these are metals, right? Metals are electropositive. So obviously these alkyl groups will become negative. So these becomes the electron donors. Okay. The third type, that is ambidentate nucleophile. What is that? Ambidentate, we talked about that. Those are flexible. Here the ambident nucleophile are the one which are having two sides of electron rich center. Is it possible? Yes, it is. Two sides of electron rich. Say for example, I am having Cn minus. Okay. So here carbon which is having negative charge and the nitrogen that is having lone pair. So this side also it can act as a nucleophile, and this side also it can act as a nucleophile. One, if that is attached with carbon, then the product will be cyanide, and if that is attached with nitrogen, then the formation will be isocyanide. So there are this kind of ambident nucleophiles are also exist. NH2OH or nitro group, which are having both the sides attack. Okay, so we talked about nucleophiles. What about their mechanism? In nucleophile substitution reaction, we have 3 different types of mechanism. These are important I'm talking about. They have many: SN1, SN2 and SNAR. What is SN1? As the name indicates, S stands for substitution, N stands for nucleophilic, and Y1 stands for unimolecular. What is unimolecular? We talked about the rate of the reaction, right? In chemical kinetics, rate of the reaction. In SN1 reaction, the rate of the reaction is 1, because in the rate determining step, only one reactant is responsible for finding the rate. Let's go in detail. This type of mechanism follows 2 steps. Step 1 is formation of carbocation. Step 2 is attack of nucleophile. We know about carbocation very well from our last video. Now, let's go step by step. First, let's talk about the step 1. Formation of carbocation. Right. So, let me take a carbon which is having just 3 substitutions. Okay. So let's say this is OH and this will be getting replaced. So on the side I'm having RRH. Okay, so the first step, that is rate determining step. Why that is rate determining step? Because that is a slow step. So carbocation formation will lead to a carbon structure like this, isn't it? So remaining OH left the compound. Okay. As a second step, we know that is a attack of nucleophile. So I'm taking the same carbocation which is having a empty orbital. So let me write it. Empty orbital like this. So what can happen over here? That is more important in case of stereochemistry part. So what can happen? The incoming nucleophile can attack on both the sides. It can attack left side or it can attack right. Okay, so it can go about attacking this empty orbital, or it can go by attacking the another empty orbital. So what kind of products we can expect? So one thing, if that is attacking to the left, the product would be like this. That's it. So if that is attacking on away from that another lobe, then the product is like this. What about if it is attacking on this side, right side? Then the product becomes like this. So this is on right and that is on left. So what would be our product? What would be our end product? Here the twist is these are enantiomers. So both the side attack can be happen. That's why one is retention in configuration, another one becomes inversion in configuration. Overall, it can form a racemic mixture out of this. Okay. So it's depend on which side the attack is happening, which side is favorable for the given substrate. Okay. So that is about the stereochemistry of SN1 mechanism. And talking about the kinetics part, the rate is proportional towards Rx, the substrate, the reactant reaches 2. So the rate becomes is equal to like this. So the energy profile diagram for SN1 becomes, I'm writing it versus energy to reaction coordinate. So it will start, reactant will start and reaches a transition state and an intermediate and again a transition state to give the product. Right? So this intermediate, that is carbocation intermediate, this is transition state 1 and this is transition state 2. Transition states are very short-lived when we are compared to the intermediates. Okay, this is also important. So what are the factors can affect SN1 reaction mechanism? The first factor is, of course, nature of alkyl group. Because you have to remember one thing, the carbocation formation step is very important in this mechanism. So stability of the carbocation determines the rate of the reaction. So tertiary carbocation is more favorable, then secondary, then comes primary, then methyl. Okay, so you have to take care of that. And the second thing is nature of leaving group. Nature of leaving group. So here you have to consider the size of halogens which are leaving the group. For example, here if I am talking about RF, RCl, RBr and RI. So the leaving capacity is more for I, then comes Br, then comes Cl and then finally F. Okay. If the acidic strength is more, then the leaving capacity is also becomes more. Weaker the base, more the leaving capacity. And most importantly, the third point is nature of solvent. How solvent presence is taking a huge role. Here you have to consider only the polar protic solvent. So which facilitates the carbocation formation very easily. How it becomes? Because it can form a bond with our leaving group and then it leaves eventually. And the concentration is concentration of nucleophile. Some questions can be asked from this part. What will happen if I am changing the concentration of the nucleophile? It will not affect the rate of the reaction. So the rate is independent of concentration of nucleophile. Why? Because it is not taking part in the rate determining step. Okay. So these are important in case of SN1. If I am going to talk about SN2, you must be aware of SN1. Because it is just opposite. SN2, that is bimolecular, and it follows a single step mechanism. How it will give product? Let's see. For example, here I am taking CH3, CH2OH, reacting with HX, it is giving us CH3, CH2X along with H2O. Okay, so how the mechanism follows? So let me take the same compound, CH3, H, and another H. Okay. First it will form, the nucleophile will get attack on which side? In the SN1 we talked about it can attack from either of the side, depend on that the product formation will be there. But here there is no opportunity to attack it from leaving group side. It have to attack it by opposite side. Correct. So in that case it will form a intermediate like this. We can't say it intermediate, that is just a transition state it is forming, where leaving group is about to leave and nucleophile just got attached to the carbon. Followed by the elimination of leaving group happens. The molecule will look like this. Due to the attack of opposite side, it always goes with inversion in configuration. Inversion in configuration means if one reactant is S configuration, the product will be R. Okay, so that here the Walden inversion takes place. We are not going to talk much about Walden inversion. Again, the rate of the reaction is depend on both nucleophile as well as a reacting substance, so that the order will be 2, which becomes this is bimolecular reaction. What are the factors affecting over here? The first factor, that is nature of alkyl group. We already talked about that. Here the alkyl carbocation formation is not important, so it takes where methyl comes first and then primary, secondary and tertiary. So if it is tertiary is mostly favored by SN1 instead of SN2. So why this is happening like this? Because due to the bulky group present in tertiary, which happens to the steric hindrance, so nucleophile can't attack if already the group is bulky. So the rate decreases. The second part, that is nature of leaving group. Nature of leaving group, once again, weaker the base, more will be our leaving group capacity. Same as SN1. And the third thing is effect of solvent. Solvent effect. Here, polar aprotic solvent. Difference between protic and aprotic is that in case of protic solvent, hydrogen will be present. For example, water, alcohol, like that. Here, polar aprotic solvent is most favorable, where the hydrogen is not taking part much. For example, for aprotic solvent is DMSO, DMF, acetone. So these are some polar aprotic solvent. So if I want to write the energy diagram of SN2 reaction, then the reactant starts and then it reaches the product with the only one transition state. It's same as the versus energy versus coordinate reaction coordinate. The energy diagram goes like this: reactant reaches one transition state, leads to the product. But in case of SN2, it reaches 2 transition state along with 1 intermediate formation. Okay, so this is about SN1 and SN2 reactions. So what about SNAR? AR here stands for aromatic. So aromatic groups can't undergo SN1 and SN2 mechanisms because of the partial double bond formation, which is more important question. So it undergoes SNAR, which is also called as elimination addition or addition elimination mechanism. Say for example, there are certain conditions for the benzene group to follow SNAR mechanism, that is, it should have a strong electron withdrawing group. So the electron withdrawing group facilitates the leaving group to leave the compound. So nucleophilic attack happens like this. Due to that, it will form a product. It's not a product, it's the intermediate like this. More precisely. So again, it undergoes the resonance because of electron withdrawing group. So the minus charge comes here. And once again, the minus charge moves to the another ortho position. So finally, the leaving group leaves. Like this, and then the nucleophile will occupies that position like this. So this is aromatic nucleophilic substitution reactions. So if that needs to happen, there should be a strong electron withdrawing group at ortho or para positions to the leaving group, so that the resonance will get stabilized. If that is present in meta, that's not more useful. Resonance can't happen over there. We are moving to elimination reaction. So what type of elimination reactions can happen? What are the types? Elimination reactions usually you see in dehydration reactions or dehydrohalogenation reactions, right? So one small part will get eliminated in the presence of acid or base. So these are usually the transformation of saturated compounds to unsaturated compound. For example, it will happen like this. So if I'm having the alkane like this and presence of base, heat given, so the product is unsaturated one. Okay, so it happens in the presence of acid or base, and also heat is also important in case of elimination reactions. So the examples are dehydration and dehydrohalogenation. So what type of elimination can happen? The elimination is classified into two: E1 mechanism and E2. So what is the difference? First, let's talk about E1, which is, as the name indicates, unimolecular. So what will happen? Carbocation formation will be there. So for example, I am taking a compound like this. The first step will always be carbocation formation. So leaving group leaves, then this is a rate determining step. So that becomes the unimolecular reaction. Then the second step, base attack. So the base will attack this position will take up the hydrogen. Due to that, the bond shift happens over there. The product is unsaturated one. In case of E2 mechanism, how it happens? So E2 mechanism, as the name indicates, that is a bimolecular mechanism. So that is a one-step mechanism. For example, here I'm taking a compound like this. The base will immediately attacking. The shift will happen to another carbon, so that the transition state formation would be base attack to hydrogen. So hydrogen is about to leave. So this is our transition state. So finally it is forming a product like this, along with pH and X minus. So the rate depends on both base as well as the substrate reactant. That is about E1 and E2 mechanism. Then we are moving to addition reactions. In case of addition reaction, it happens, it's just opposite to elimination. So multiple bond system like unsaturated bonds will undergo addition reactions to form a saturated compound. For example, like this. We'll see more about addition reaction in hydrocarbons chapters as well, in upcoming chapters usually. So the addition reaction happens like this. In case of addition reaction, it is having two types: electrophilic addition reaction and nucleophilic addition reactions. Electrophile, once again, electron loving species. For let's say instead of XY, I'm having Br2. So each Br will get occupied to one of those carbon. So for example, it will, the Br first attack electron rich, first attack the Br, so another Br will leave the compound, forms a carbocation. Next, the eliminated one attacks the carbon, so that the product will be like this. This is electrophilic addition reaction. But in case of nucleophilic, say for example, I'm taking R, C double bond O, R dash, reacting it with nucleophile. The nucleophile first attack the compound, so that the product goes via R dash. In case of nucleophilic addition, I'm taking an example of R, C double bond O, R dash. Nucleophile, along with that hydrogen is there. So nucleophile is electron rich, so this is attacking the carbon, so the product goes via O minus, and then nucleophile with R dash. Further, H plus is there, so this oxygen take up the H plus, so the product is OH R dash. So this is a nucleophilic addition reactions. So today we dealt with substitution, addition and elimination reactions as well. If you have any doubt, please let me know. Please do more practice of questions. The next session we are going to deal with hydrocarbons, with alkanes, alkenes and alkynes, with other reaction mechanisms like what is Sesef rule, what is Markovnikov's rule, anti-Markovnikov, and etc. Stay tuned. Thank you. Hello everyone. Welcome to fourth session of this ChemCrack course series. Today we are going to see some important and interesting part of organic chemistry, that is none other than isomerism. So isomerism, it is not a separate chapter. It is linked with GOC, General Organic Chemistry, but it is very, very important to learn about this to solve other problems of organic chemistry, right? I know most of the students are worrying about this part, isomerism. You may miss the class, you may forget about the silly things about isomerism. In this today's session, we are going to crack that. We are going to ace the isomerism chapter. By end of this session, you'll be master in organic isomerism. Okay, so without any further delay, let's get started. First of all, what is isomerism? Iso means same, right? Merism there means parts. So isomerism means there will be some similarity, but same element in between two compounds. What are they? Let's take it out. So isomerism is broadly classified into two, that is structural and stereo. Today we are going to see both the isomerism. First, structural. It is very, very, very simple. Okay, but questions can be asked from this part a lot. Structural isomerism, as the name explains, the structure varies. Same molecular formula, but different structural formula, different way of writing it. Okay, so that is structural isomerism. This is further classified into main 6 types. They are chain isomerism, that is having same molecular formula but different arrangement of carbons credited. How, ma'am? Yes, we'll come to that. Chain isomerism, you can see the examples over here, that is pentane and isopentane. Pentane, you can write how many carbons? 5 carbons, CH2, CH2 and CH3. Talking about isopentane, iso means 2 CH3 group attached with 1 carbon, isn't it? So isopentane structure is CH3, CH, CH3, CH2, CH3. Right? What is the molecular formula of isopentane? 5 carbons are there. How many hydrogens? 3, 6, 7, 8, 9, 10, 11, 12. C5, H12. What about pentane? Once again 5 carbons and how many hydrogens? 9, 9 plus 3, 12 hydrogens. Right? Same molecular formula but different way of attachment in the same chain. Chain isomerism is exhibited by only the carbon chain. No other functional groups are changing. No other substituents are changing. It's just talking about the hydrocarbons. Please be careful with that. Okay. So the second part, that is position isomerism. That is having different positions of functional groups. That is very, very important. Different position of functional group. Let's say I'm having a functional group of alcohol, which is attached in second position. CH3, CHOH, CH2, CH3. What is this? 2 butanol or butane to all. Let's say I'm attaching this functional group in third or first position, let's say. Then that will become 1 butanol, right? I just took that OH and attached to it first position. That's it. I'm not literally taking it, but the change in position of the functional group is called positional isomerism or position isomerism. That is second type. The third type is functional isomerism. What is functional group? Amines, OH, COOH, aldehydes, ketone, amides, those functional groups, right? Other substituents as well. if the functional group changes, how the functional group will change. For example, here you can take alcohol and ether. Let me give you the example of, I'm going to erase this. If you are not noted, please note this down. Functional group, what is the general formula of alcohol? That is OH. What is the general formula of ether? Yes, that is ROR, right? So if I am taking alcohol, CH3, CH2, CH2, OH, this is propanol, right? Alcohol functional group. What is the molecular formula of this? Which is C3H8O, correct? If I'm writing it as an ether functional group, then that will become CH3O, CH2, CH3. What is the name of this? Methoxyethane. Ether functional group with, what is the molecular formula? C3H8O. Same molecular formula but different functional group. That is called functional isomerism or functional group isomerism. Is it clear? Yes. Now let's move on to the confusing part, so-called confusing part, but it is not. That is metamerism. Remember this, guys. Metamerism is exhibited by the functional group which is having two hands of alkyl groups. What is that, ma'am? What is two hands of alkyl group? Let's say I am considering alcohol. What is the general formula? ROH. Only one R group is attached with that. If I am considering ether, ROR, two functional groups are there. Oxygen is attached with two alkyl groups. That is having two hands holding the alkyl group, right? Metamerism only exhibited by the compounds like this. I can give you another example like ketone. Right? So the metamerism is exhibited by these kind of groups, not for RH or RCOOH or RCHO, RNH2, nothing. Only the functional group which are having two hands. Is it clear? Most of the students do mistake in this part, particularly metamerism. I don't know why, but hope this is clear now. What is metamerism? Once again, that is having same functional, the molecular formula, but different alkyl group attached. Say for example, here I am having ether as an example, CH3O, CH2, CH2, CH3. Okay. Another isomer of same compound is CH3, CH2, O, CH2, CH3. The molecular formula is same, C4, C4, H8 plus 3, 11, 3, 14, O, C4, H14, O. H14, H10, H10O. Similarly, here also that is C4, H10O. Okay, but the alkyl groups attached with this functional group is getting differed. Here I am having methyl, this side I am having propyl. Here I am having ethyl, another side I am having ethyl. Okay, so please be careful with that. Next functional group, that is tautomerism. What is tautomerism? I am explaining to you with an example. Tautomerism is a reversible thing. Okay, a molecule can go with product side or reactant side like an equilibrium. Okay, say for example, if I am having acetone, CH3, CO, CH3, and if I am having propane 2-ol, how many carbons? 3 carbons must be there. Propane 2-ol. Okay, so how many carbons? 3 carbons. C3H6O. This is also C3H6O, right? Same molecular formula once again. But what happened over here? The shift of hydrogen. This maintains an equilibrium. This is keto and this is enol. The shift of hydrogen happened over there. So it will get cleaved, O becomes negative, so hydrogen get attached with oxygen. So keto-enol tautomerism. Similarly, we have nitro-acinitro tautomerism. But mostly they will be asking about keto-enol tautomerism. You must have seen this in mechanism part. Okay. The last type of structural isomerism is ring chain isomerism. That is very, very simple. If I'm writing it in chain, I can write it in ring model also. How? Let's say I'm taking propene. Cyclopropane. CH2, CH2, CH2. How many carbons? 3 carbons, 6 oxygen. Right? How many carbons over here? 3 carbons. Sorry, talking about hydrogens. How many hydrogens? 6 hydrogen. So C3H6, same molecular formula. I'm writing this is ring and this is chain. Sorry. The next part, that is very simple isomerism type, that is ring chain isomerism. Ring. For example, if I'm writing cyclopropane, CH2, 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 C3H6. If I'm writing propene, CH2 double bond, CH, CH3. The molecular formula is C3H6. Same molecular formula I have written as ring structure and this is chain. Okay. So this is ring chain isomerism. The questions can be asked from this part for this year. So please be prepared. What is isomerism? That is very, very important point to be noted here is where you will get confused. That is metamerism is sorted. Functional group isomerism is sorted. Positional isomerism, that is very, very, very important. It's meant for functional groups only. Metamerism is meant for the functional group which are having 2 sides to hold their alkyls. Okay, so hope this is clear. If you have any doubt in isomerism, please let us know. We explain it in detail as a separate video. Now let's move on. The next part of isomerism is stereoisomerism. Stereo is not like sound. Stereoisomerism is having different spatial arrangement. Where that is arranged. Structural isomerism is how that is arranged. This is where that is arranged. This is having the further classification of conformational and configurational. Guys, please be aware, conformations and configurations are entirely different. Conformations are the one which are having different spatial arrangement due to rotation about sigma bond. Okay, so let's see this in detail. First, configurational isomerism. Here, I am going to take geometrical isomerism first. What is geometrical isomerism? It is having restricted rotation. It is having restricted rotation. What is restricted rotation? Let's say I am having double bond CH2, CH2. Can I rotate this molecule? Is it possible? there is lots of strain, there will be a restriction to rotate this molecule, isn't it? I'm not talking about the rotation in this wise. I'm just talking about the rotation over here. Right? So that restricted rotation is about geometrical isomerism. Let's have some examples of geometrical isomerism so that you'll be very clear about that. For example, if I'm taking C double bond C, A, and this is B, and this side I'm having A and B. Okay. Can I rotate it in this way to form B, A, A, B? Guys, please be aware, I'm not talking about rotating the entire molecule, I'm just talking about rotating one side. Okay. So can I get this molecule by rotation? Obviously not, right? Because the rotation is restricted because of the double bond. So this is not possible, which makes this is a different molecule and B is a different molecule, right? So what would be the name of these? Let's name this, depend on the attachments. So here we have two type of configurations. The first one is cis-trans isomerism. This is if the two similar groups are on the same side of restricted rotation. Then the configuration is cis. Say for example, if I'm taking a molecule of this, two groups are on the same side, then that is cis. If that is an opposite side, what does this mean? Then that is trans. Then that will be considered as trans. As simple as that. I'm having a double bond. I'm having a group, similar groups which are attached on the same side, then that is cis. If that is attached on the opposite side, then that becomes trans. Okay? Similar group, note it down. What about the other classification? That is E-is-it. E-is-it isomerism. What is the difference between these two? Once again, this is also deals with the restricted rotation. This is also deals with the double bonds and where the restricted rotation are possible. Here, the important point is seniority of groups. Seniority of groups. What is seniority of groups? Say for example, if I am having Cl, I, H and Br. Let's take one carbon and consider these two substituents, hydrogen and bromine. Among these two, which is having highest atomic number? Of course, bromine. So I'm ranking it 1. Hydrogen will get second rank. Considering another carbon, Cl and I, which is having highest atomic number? Obviously, iodine. So first rank goes to iodine and the second rank goes to chlorine, right? So depend on this seniority of the groups. If that is positioned in the same side, then that is Z. You can remember it like same. This is also having the same sound. Z is also having the same sound. Okay, Z. Just remember it like that. So if that is on the same side, then that is Z. If that is on the opposite side, the high priority groups are high priority groups are on the opposite side, then that is E. This is 1 and this is 1 which is on the opposite side. then that is E. E for opposite side. Is it clear up to this part? Cis trans Ez. Okay. Is there only one way for mentioning geometrical isomerism? None other molecules are having any restricted rotations? No. There are some molecules which are having restricted rotation. The most important one is rings. For example, if I am taking cyclopropane that is attached with the substituents A and B, how it will undergo rotation? How that will undergo rotation? It's not possible, correct? So in that case, how it will form this kind of molecule B, A and A, B? This is not at all possible, which means that this is having restricted rotation. So this can also be possible in geometrical isomerism. Other than this, one ring system which is having a double bond or which is having lone pairs of double bond, this system is also possible. Okay, mostly they will be asking questions from rings and double bond. So, hope this is clear as far as now. Then we are moving to next part, that is RS notations. Naming R and S for molecules. We are naming it under the rules which is called can in whole prolonged rule, that is CIP rule. Okay, what this rule says? The first rule is that the group with the first atom having high atomic number is the senior. High atomic number, what we have saw in other examples also. High atomic number, that is priority 1. That is first rule. The second rule is higher mass isotope. Let's say I'm having isotopes for let's say hydrogen and deuterium, hydrogen and tritium, deuterium and tritium. So high masses, high mass isotope, that is senior, that gets more priority. Okay. The third rule is if I'm having a situation of the first atom of a molecule is same, CH3, CH2, the carbon which is same, the atomic number becomes same. In that case, I have to go to second atom. First atom same, then we have to move to second atom. Fourth rule, groups containing double and triple bonds are assigned seniority as both atoms are duplicated or triplicated of that. If I'm having double bonds, which means that I'm having two molecules of same. If I'm having double bond CH2, then I should consider that as I'm having two CH2 over there. If I'm having triple bond over there, triple bond CH, then I should consider that as three molecules of CH is present over there. Depend on that, I have to give the seniority. And rule number 5 is bond pair is more senior to lone pair. Bond pair is senior or gets high priority than lone pair. Don't be scared of seeing these rules. It's just very, very simple. While solving the problem, while solving these examples, you will get to know. And there is a special rule I'll let you know while solving problem. Now, solve this problem to get to know these 5 rules and secret rule better. Before that, I would like to let you know R is for clockwise and S is for anti-clockwise. Okay, why I'm talking about the rotation now? Let's take it out. Here I'm having the first example. Hydrogen, COOH, CH3Br and Cl. So which will get more priority? Obviously, the first priority will go to Cl. Considering COOH and CH2Br, which will get more priority? Both are starts with carbon. So we have to look for second atom. That is rule 3 says, right? So second atom here, that is what? Here the second atom is bromine and hydrogen. Don't misunderstood, that is hydrogen. Don't do this blender over there. That is Br. Because you can see this is attached like this. Carbon attached with Br. So you can take Br as a second atom attached over here. Okay. So what about here? COOH. Carbon is attached with double bond O and bond OH. Right? So the second priority goes to CH2Br. So the third priority is carboxyl group. And the fourth priority is hydrogen. Now, one rule you have to remember, that is you are going to find the path, whether that is clockwise or anti-clockwise. In the journey, you have to remember one thing, you have to go via 4, not via 3. Okay? If 2 is not available. Here, 2 is readily available nearby. So you can go by this way to reach 1. Whether that is clockwise or anti-clockwise. Is it clockwise or anti-clockwise? This is clockwise. So it becomes R. Right? So let's go to second example. Once again, the priority groups become same because I just took a same example in different position. But the groups are same, so the priority order will be same. Will that change the notation? Let's see. Cl, CH2Br. Okay. So I can go like this. Is it clockwise or anti-clockwise? It is clockwise. It should be R, but it is not. Why? There comes the sixth rule. Sixth rule says that if there is a fourth priority group on front of you or above the plane, you have to reverse the notation. So I can simply write the least priority group must be behind the plane or far from you. Ma'am, how to find above the plane or behind the plane over here in this kind of Fisher projection? In that case, you can take hydrogen must be in vertical position. Okay, hydrogen must be in vertical position. I mean, the least priority group must be in vertical position. Here that is in horizontal position. So I have to just reverse the notation. It becomes yes. And the third example over here, that is which is having 2 carbon system. If I am considering the first carbon, which is green color, you have to take this group as a single group like we took for COOH. Okay, so in that case, which will get more priority? COOH or nitrogen group? Obviously nitrogen, because nitrogen atomic number is 7, carbon atomic number is 6. So first priority goes for nitrogen, second priority goes to COOH, third priority is for the group below, and the fourth priority is hydrogen. So least priority group must be in vertical position. Here that is not same, so I have to just do the opposite. Before that I have to find the clockwise or anti-clockwise, right? So this is clockwise or anti-clockwise? This is clockwise. Clockwise must be R, but I have to use the reverse rule. So this becomes yes. So let's take another number of degrees of rotation observed when the compound is passing the plane polarized light. Okay, how much it is showing that rotation. Here we have the formula for that. Specific rotation alpha, which is equal to theta divided by L into C. Here L stands for path length and C stands for concentration. Theta is observed angle of rotation. Okay. Sometimes they will give you the values of path length, concentration and the rotation angle. They'll ask you to find the specific rotation. So please be prepared for that. So this kind of question can be asked. And now let's move on to another important part, that is chirality. What is chirality? A compound which is non-superimposable to its mirror image. That is called chiral. Non-superimposable to mirror image. That is chiral. Okay. While a compound is superimposable to that mirror image, then that is called achiral. If that is superimposable, then becomes achiral. So how we can find that? We can find the chiral center. So what is chiral center is that? A compound in which carbon is attached with 4 different groups, which is lacking for symmetry, is called chiral carbon or asymmetric carbon. Lack of symmetry, we do have plane symmetry, plane of symmetry, axis of symmetry, and center of symmetry. Which lacks for symmetry, then that is asymmetric carbon, and if that is attached with 4 different groups, this attached with 4 different groups. I'm talking about carbon, that's why I'm mentioning 4. 4 different groups, then that is chiral center or asymmetric center. Flakes of symmetry means asymmetric center, attached with 4 different groups means chiral center. We'll see the example. For example, if I'm taking a carbon that is having 4 different groups. This is chiral carbon, which can be denoted by the symbol star. Okay. Similarly, the asymmetric carbon can be denoted by the symbol star. Now we are moving on to the another important part, that is different type of writing a molecule. Different type of projections. Projection formula. What are the different types of writing a molecule? For example, we have wedge dash. We have Fisher projection. We have Newman projection. We have Sohas projection. These are different methods of writing a compound. First, what is wedge dash? Wedge dash is writing it with the 3-dimensional system of, let me write it here, carbon. What are these? So here the simple dash refers for that substituent is in the plane it's on the surface, is in the plane. If that is denoted by like this, like wedge or dotted lines, then that is behind the plane or far from your way. Behind the plane. If that is mentioned as solid wedge, the former one is a dashed wedge, this is solid wedge, then that is above the plane, it's towards you, that is wedge dash. Talking about the next projection, that is fissure. Fissure projection of writing is writing as a cross. For example, we saw that in RS notation as well, like this. Here how we can find it out whether that is above the plane or behind the plane. So which can be denoted as like this. The horizontal ones are above the plane and the vertical ones are below the plane, which is equal to this. G, COOH and H. Okay, that is fissure projection. Moving on to the next part, that is Saha's projection. Saha's projection is a molecule viewed slightly above, like top angle view, like this, like this. This is kind of a top angle view of the carbon attached with the substituent. The final projection, that is Newman projection. Newman projection, which is like man standing over here, which represents the front carbon and the back carbon, like this. Here I am having two carbons. What are they? The first one, let me take the dot, the green one, which is represented by a dot, and I'm taking another one as in pink, which is here, that is round, right? So the dot one, the point, is represents the group attached with near to the eye. Okay, it's towards you. The dot is towards you. And the circle represents away from you. Behind plane is away from you. That is rear carbon. Okay, so that is Newman projection. How we can convert this? How we can do the conversions of one projection formula to another one? If you want, we'll do that in detail. Now I'm giving you just a simple example of this. For example, if I'm taking 2,3 dimethyl butane. Butane, so 4 carbons must be there. 2,3 dimethyl. So remaining hydrogens. For this structure, we are going to write all other projection formula. First, let's start with wedge and dash. Here I am having 2 carbons. Okay. So let's say I am having hydrogen on the behind the plane, 1 CH3, it's on solid wedge, which is towards you, and for another carbon, hydrogen is towards you, CH3, it's away from you, and 1 is on the plane. So I took wedge dash like this. Okay, depend on that how we can write it for other projection formulas. Okay, I'm considering these two carbons as a main carbon, front and rear carbons. So now let's go to the second projection. I have the lines. So this and this carbon, one carbon is attached with two CH3s and one hydrogen. Okay. So here I'm having CH3. So CH3 with CH3, right side I'm having hydrogen, left side I'm having another CH3. Note it down. These are opposite to each other. The wedges, solid wedges are opposite to each other. So how we have to write the opposite pair? That is one CH3 to another CH3 is just opposite. So CH3 opposite side, and then to that CH3 I'm having hydrogen and another dashed wedge CH3. Now let's go to the third projection formula. Here I'm considering CH3, this CH3 and another CH3 must be on the same side, or I can write it in the opposite side if I am writing like this. Both the CH3s are opposite, hydrogen are opposite. So because while doing the rotation, I can get it on the same side. That will equals to this direction. Right? Clear? So now let's see Sawhorse projection also. So front and rear carbon. So front carbon, that is dot. So I'm taking CH3, this guy, and then CH3 on left side, hydrogen on right side. And if I'm considering the rear carbon, that is circle. So CH3 goes on the top and another CH3 on the right, hydrogen on the left. Okay, so this is as simple as that. I will tell you, you can work on 2-bromo, 2-chloro-butane, and let me know if you are facing any problem while doing 4 other projections for this compound. What is optical isomerism? We all know it comes under the category of stereoisomerism. Stereo means difference in spatial arrangement, right? Optical isomerism is a form of stereoisomerism where the molecules have identical molecular formulas and bond connectivity but differ in 3-dimensional spatial arrangement. Most importantly, it results in non-superimposable mirror image. Okay, so if you are matching those mirror image, it will not match. That is what the non-superimposable mirror image is. Okay, so that is what optical isomerism. The molecules are the compounds which exhibit this property. Those are called optical isomers. Okay, so without getting much detail about it, I just want to give you the terms we are using to explain this optical isomerism. Okay, the first term, that is chiral carbon. Chiral carbon, asymmetric center. These two are the different words. Chiral carbon are the carbon atom which is attached with 4 different molecules or atoms. Say for example, I'm having carbon attached with hydrogen, iodine, fluorine, and another side CH3. 4 different groups are attached with carbon, that is chiral carbon. This is mentioned as star, asterisk symbol. Okay, and this is called stereo center or asymmetric center. More importantly, asymmetric means if the carbon or the compound is lacks of symmetry. There are different types of symmetry: plane of symmetry, axis of symmetry, center of symmetry. We are going to see about that. Okay, if a compound lacks these symmetrical property, then that becomes asymmetric. Those are called asymmetric carbon or asymmetric center. Okay, here this carbon is asymmetric carbon. Our next part is that optical isomers. Optical isomers are the molecules which can rotate the plane polarized light. What is plane polarized light? That is our normal light, white light, which is having vertical and horizontal waves in it. Okay, so which will be looking like, let's say this is the plane. It would be better if you are imagining it in three-dimensional way. The vertical lines and the horizontal waves as well in case of our normal light. But in case of plane polarized light, we are producing it through passing the white light into nickel prism and polarizer to make it as a singly arranged waves. Waves are in only one direction. Okay, that is plane polarized light. So if an isomer exhibits optical isomerism, then it can rotate the plane polarized light either clockwise or anti-clockwise. If that is rotating in clockwise, then that is called d-isomer, also denoted as plus symbol. Okay, if that is rotating that as an anti-clockwise, then that is L-isomer, denoted by minus symbol. Okay, so which can rotate plane polarized light to clockwise, that is d-isomer, which can rotate plane polarized light to anti-clockwise, that is L-isomer. This much clear? Yes. I said the word rotate. So rotation means the angle changes, right? So how much it is getting rotated? Let's say I'm using a molecule tartaric acid or any optically active molecule. How much rotation is happening, either clockwise or anti-clockwise? That rotation we are talking about here in case of specific rotation. It measures the optical activity. And how it is calculated? Specific rotation is alpha, and this is calculated by alpha L into C into 100. Alpha by L into C into 100. Here alpha is observed rotation when we are passing the molecule into plane polarized light, and L is the path length in decimeters. C is the concentration of the solution. Okay, this rotation is observed using a polarimeter, that instrument, and it can be of positive, dextrorotatory or levorotatory. This kind of question can be asked to apply this formula. They will give you observed rotation, path length, concentration and all. They can ask you find the specific rotation. Okay, so that kind of question can be asked. Let's move on to the next part, that is types of stereoisomers. Types of stereoisomers, we talked about optical isomers, we talked about conformations. Here, enantiomers and diastereomers. What are these? These are very simple. That if that is an enantiomer, then the molecules are, the mirror image of that molecule will be non-superimposable. Non-superimposable mirror images are called enantiomers. They'll have identical physical properties. Physical property means color, smell, what we can observe it without doing a reaction, and those parts of physical properties, they will have identical physical properties except the rotation of plane polarized light. It can be of D or it can be of L. And interaction with their other chiral molecules. How it will interact with other molecules. What is this word chiral over here? Chiral means the same. I told you, right? Stereo center or chiral center. Chiral means a carbon which is having 4 different groups attached to it. And enantiomers will have equal and opposite specific rotations. D and L pair are considered as enantiomers, but they should be of mirror image and non-superimposable. Talking about diastereomers. Diastereomers are the stereoisomers which are not mirror images and not superimposable also. They are neither mirror images nor superimposable. They'll have different and chemical properties entirely and can occur in molecules with multiple stereocenters. They can have multiple, more than one stereocenters. We'll see the example. For example, if I am taking a molecule like this, HCl, HCl, C2H5. What about the mirror image of this molecule? Once again, this will have CH3, C2H5 will be on the same position. Cl will come here, H will be here, Cl and H. These are mirror images, but is it superimposable or non-superimposable? For example, if I'm taking this molecule and trying to match with the original one, is that matching? No. Cl and hydrogen are in different positions, right? So, which means that it is non-superimposable. Okay, so these two are enantiomers. Enantiomers. It can be of D and L. Talking about diastereomers. For example, if I am taking a molecule, let's say I am taking the same molecule and a pair of this diastereomer will be there shouldn't be a mirror image, right? So it can be like this. So these are not mirror images, and as well as these are not superimposable also. They are diastereomeric pairs. Okay, if examiner gives you a molecule, check with these conditions and put the right answer whether that is enantiomer or diastereomer. Now we are going to see the next part, that is elements of symmetry. We have different symmetric properties. As I told you earlier, what is asymmetric center means? If that lacks of symmetric property, then that is asymmetric center, right? Asymmetric carbon. What are those symmetric properties? In general, we have these three important symmetric properties, that is plane of symmetry, center of symmetry and axis of symmetry. Plane of symmetry is very simple. Let's say I'm taking a molecule which is having two stereogenic centers, let's say. And I'm having these H. So from here, these two are mirror images to each other, isn't it? So this is mirror image. So both the sides we can see the same molecule. That is plane of symmetry. If we divide the molecule into two identical halves, the mirror image relationship between there in this compound, right? This is plane of symmetry. Although the four different groups are attached to the carbon, since that is having a plane of symmetry, this compound is not optically active. Okay, and the second one is center of symmetry. Center of symmetry means from the middle line, how the symmetry occurs. For example, if I'm taking a molecule like this, the simple molecule, let's say I'm taking a simple CO2 molecule, simple CH2CCH2. Okay, so here I'm having central carbon, and both the sides from this point I'm finding the same compound, same molecule attached to it, and another side also I'm finding the same molecule. So which means that is having center of symmetry. Okay, so that is one symmetric property. And the third one, that is axis of symmetry, means if I'm rotating one side of a molecule, I should get the same thing. Let's say The simple molecule, I would say, that is H2O. Okay, let's say I'm HA and this is HB. I'm naming it, these hydrogens. So I'm rotating it on one side. It will become HB and HA, isn't it? Once again I'm rotating it. I'll be getting the same molecule again. So the rotational axis that produces the identical arrangement multiple times per 360-degree rotation, then that is having axis of symmetry. Why these are important means, depend on this we will find whether the compound is optically active or not, whether the compound exhibit optical isomerism or not. Okay, so this is some basic thing. Mostly they will be asking questions from plane of symmetry. We applied this concept in another compound, that is called meso compounds. Meso compounds are the one which are having chiral center, but that is optically inactive because of the cancellation of optical activity, that is because of plane of symmetry. Okay, the same example as here, I am taking tartaric acid. So this is having a plane of symmetry, right? That's why it makes this compound optically inactive. That is very much important. Meso compounds are optically inactive, although they are having chiral centers. But what if that is having odd number of chiral center? Optically activity may come, but this is common where the even number of chiral centers are there, even number of stereo centers are there. Okay, and finally another term, that is racemic mixture. Racemic mixture is nothing but, we talked about D and L isomer, which can rotate clockwise, that is D, and which can rotate anti-clockwise, that is L, LIBO and extrorotatory, right? So if a compound that consists of both the mixtures, both the compound or both the isomers together, that mixture is called racemic mixture, but that should be of equal amount. Let's say if I'm having 50% of D isomer, then I should have 50% of L isomer. The equimolar mixture of D and L isomers are called racemic mixture. Okay, and what will happen to that optical activity means, it will become optically inactive because of external compensation, which means D isomer is plus isomer that rotates on one side, L isomer is minus isomer that rotates the plane polarized light to another side, which will cancel out each other, right? Racemic mixtures are optically inactive because of external compensation. Meso compounds are optically inactive because of internal compensation. Clear? Now let's move on to how to find number of optically active compounds or optically active isomers in a given molecular formula or given structure. Okay, there are three different formulas we have, these different possibilities we have. The first one is unsymmetrical molecule. It is not at all having any symmetry in it. No plane of symmetry, no center of symmetry, no axis of symmetry. Then you can use the formula of 2 to the power n. N refers to chiral center. It can be of any number of carbons. 2 chiral center, 3 chiral center, 10 chiral center, it can be of anything. So number of optically active isomers become 2 to the power n. And out of this, which is meso form, we said that is not possible over here, they are unsymmetrical. And the racemic mixture becomes A by 2, which means if I am getting 10 optically active isomers means 5 will be racemic mixtures. The total isomers are A plus M, that is 2 to the power n only. Okay, the second case, that is symmetrical molecules with even number of asymmetric carbon. Even number means 1, 3, 5, 7, etc. In that case, you have to use the formula. The total optically active isomers are 2 to the power n minus 1. Once again, n is for chiral center. The mesoforms will be 2 to the power n by 2 minus 1. And the racemic mixtures, which is A by 2, total isomer A plus M, optically active isomer plus mesoforms. And finally, the third category, that is symmetric molecule with odd number of asymmetric carbons, like 2, 4, 6, 8, and etc. In that case, optically active isomers would be 2 to the power minus n minus 1 minus 2 to the power n by 2 minus 1 by 2. Okay, here this part belongs to meso compound, and total isomers become 2 to the power n minus 1. Okay, so kindly take a screenshot of these formulas. This will be very useful while you are solving this kind of problems. Okay, then we are moving on to optical activity without asymmetric carbon. You said it should have a chiral carbon, it should have an asymmetric center, but how a compound can exhibit optical activity without having those centers? Yes, that is possible. Those molecules are allenes, spiranes, biphenyl with restricted rotation, some metal complexes. Here, these names are important. Okay, I'll give you the structure. So if an examiner is giving you the structure, then you won't be able to answer this question if I'm not giving you the structure. The first one is allenes. You can see it is having CCC in the middle, 3 carbons, and A and B, the different molecules or atoms are attached. Here, how it becomes optically active? The first thing is, it is having a double bond in between, and these double bonds are arranged in the way perpendicular to each other. The 3-dimensional way, I should write it like this. Can imagine this carbon is perpendicular, it's towards you. This B is away from you, A is towards you, and these two are in the plane. It takes out a different 3D arrangement. That's what the optical isomers are, right? So that makes allenes with odd number of carbons become optically active. What will happen to even number of carbons in allenes? Then that will become optically inactive, because that will get cancelled out each other, compensation happens, that becomes optically inactive. Okay, the next example is spiranes. Spiranes are nothing but replacing the double bond with the spiral structures, like replacing it with this kind of structures, and biphenyls with restricted rotation. Say for example, here I am having biphenyl CH2 S double bond O, another phenyl ring. So these are having biphenyls, but the carbon that becomes optically active because of the tetrahedron shape, because the attached groups are different. Some metal complexes, we'll see that in coordination chemistry chapter. Point to be noted here is allenes, spiranes and biphenyls are optically active even though that is not having asymmetric carbon. Then we came to an last part of this session, that is conformational analysis or conformational isomerism. Here I just want to give you the important points to be noted. The first of all, conformations is due to the rotation around the single bonds. There is no work for the double bond, triple bond sections. Only the rotation due to the single bonds. Okay. Say for example, I am taking ethane. CH3, CH3. Is there any double bond? No. Is there any possible rotations? Yes. I would like to represent it like this. With this is front carbon and circle is rear carbon. We saw that in last class. Sorry. H, H, H. There are two types of arrangements over here for this conformations. I mean, there are two types of conformations we can have for ethane. One is that staggered, another one is eclipsed. This conformation is called staggered, and the eclipsed will be look like this, which is having the bond angle or dihedral angle between the atoms will be very, very less when we are compared to staggered. Out of these, which will be more stable? Staggered will be more stable than eclipsed. Okay, because in case of eclipse, the repulsion can happen, which makes it less stable than the other conformation. Similarly, you can draw that for butane as well. Butane, CH3, CH2, CH2, CH3. If you want a detailed analysis of butane, let us know. Here the front and rear carbons to be taken in these two carbons. Okay. The one of those conformations will be looking like this. Here, for the staggered and eclipsed, we do have other arrangements as well. I'll give you the most stable conformation of butane, that is anti-conformation. Both the CH3 groups are opposite to each other. The anti-conformation, which is more stable in case of butane. Other conformations are fully eclipsed and gauge, partially eclipsed. Those will be there, but out of those, anti is more stable because both the CH3 groups are opposite to each other or anti to each other, so the repulsion or the dihedral angle will be very less, which makes it much more stable. Then cyclohexane. Cyclohexane means what? Ring which is having 6 carbons, right? So this type of arrangement, this type of structure for cyclohexane is much more congested, much more strained. For that we can write it in different way. Out of one way is this, which is called boat and chair. This is chair and this is boat. Out of these two, which is more stable? Chair conformation becomes much more stable than boat conformation because it eliminates the axial and equatorial bond strain and repulsion, and those stuffs are there. This part we can go in detail, but it will take more time. It involves lots of concept. So I want to make it short. I just want to tell you, chair conformation is much more stable than the boat conformation. That those kind of questions only we can expect from JEE Main and NEET. Okay. So by this, we just finished the theory part. Let's see whatever we have learned, can we solve those questions through this? Okay. So the first question is about which of the following compounds will exhibit geometrical isomerism? The option A, 2-phenyl 1-butene. Quickly we'll draw the structure. 1-butene and 2-phenyl. And 1,1 diphenyl 1-propene. This is A. B is 1-propene 1,1 diphenyl. And C is 1-phenyl butene. 1-phenyl 2-butene. 1 phenyl, 2 butene, and D, that is 3 phenyl, 1 butene. 3 phenyl, 1 butene. Okay, so out of this, which can exhibit geometrical isomerism? You can see it should have a 2 different groups attached with single carbon, and it should have a double bond in it, right? Let's take option A, that is having 2 hydrogens over here. That makes it optically, it is not exhibiting geometrical isomerism. And if I'm talking about these phenyl group, then surely that is not. And what about this one? Yes, it can. So let me write it in this way. Carbon which is attached with 1 hydrogen, another CH2 phenyl double bond, another carbon with hydrogen and CH3. So this can exhibit geometrical isomerism. What about option D? That is not, because of 2 hydrogens over there. So the right answer is option C. These are previous year questions and anticipated questions for this year. Okay. Then number of structural isomers for C6H14. Structural isomers. So first write the molecule and then find out what are the different ways we can write it for this. Okay, so this is number 1, and number 2 is, I can put CH3 in the middle. CH, CH3, CH2, CH2, CH3. Third configuration, I can write it with isomers. I can write as CH3, CH3, CH2, CH3. And the fourth possibility can be CH3, CH3, CH, CH3, CH3, and the fifth possibility, that is CH3, CH2, CH3, CH2, CH3, H. Is it possible that the name of this compound will be 1, 2, 3, 4, 5. So second position I'm having, third position I'm having methyl. Here I'm having it in second position. Here 2, 2. Here I'm having it in 2, 3. So these are the 5 possibilities I can write for structural isomers of C6H14. Let's move on to this question, which is asking about absolute configuration of this structure. Here I'm having 2 carbons. Let's say this is 2 and this is 3, because we should start naming it from functional group. Okay, so let's do the absolute configuration of carbon 2. That is, it starts from OH, then it goes to Cl, then COOH, finally hydrogen. So hydrogen, which is in above the plane, which is in horizontal position, we have to do the reverse of whatever the result we are getting. So first of all, 1, 2, 3, 4. So which makes it clockwise and R. So I have to make it as yes. So 2, yes. Then the third one, I'm numbering it different color, 1, and this becomes 2, this is 3, and hydrogen becomes 4. Once again I have to do the reversal. This time this is going 1 and 2, that is anti-clockwise, which is S. Doing the reversal, that becomes R. So 3 R 2 S, that is the answer. Then next question. Acetone and propanol are what kind of isomers? Acetone, which is having keto functional group, propanol, that is aldehyde functional groups. So these are functional isomers. Then number of optical isomers of the compound. CH3, CHBr, CHBr, COOH. So how many optical isomers this compound is having? Obviously this is not having any meso compound. Okay, so this is having 2 chiral centers. So optically 2 chiral center, and is it symmetric? No, is it not? It is asymmetric. So apply the formula 2 to the power n. So n here is 2. So which makes the answer D. Let's solve this question. Total number of acyclic structural isomer possible for the compound of molecular formula C4H10O. Okay, we should not include any rings. Okay, so let's start writing it. This is 4 carbon system. So CH3, CH2, CH2, CH2OH. So number of carbons are 4, number of hydrogens becomes 7, 7 plus 3, 10. And the second way of writing it, which is, you can put the functional group in second position. CH2, CH3. The third way, it's giving the substituent at different position. CH2, OH. Fourth way, I can write it in the way of 3-degree carbon. And the fifth way of writing it will become the different functional group. Is it possible? We know the functional isomer of alcohol is ether. So let's try out that way. CH3, CH2, OCH2, CH3. How many carbons? 4. How many hydrogens? 10. And 1 oxygen. Okay. The next way, let me write the different isomer of the ether. It is the metamer of this ether. And the another metamer is, kindly check number of carbons and hydrogens are sorted. Yes, so these are the possible acyclic without any ring. I can write the structural isomers of this molecular formula, that is 7. Now let's move on to the next question, that is asking for meso compounds do not show optical activity is because we know not very well, right? They do not contain chiral carbons. Yes, they do have. They have non-superimposable mirror images. They contain plane of symmetry. They do not contain plane of symmetry. They contain plane of symmetry. So that is the answer for this question. Optically active molecule is among these 4. So let's analyze it one by one. Is it optically active? No. This is having plane of symmetry. This becomes meso compound. So this is not. And what about this? This is also not because of plane of symmetry. And what about this one? Here you can see COOH and COOMe. So which makes it different? And final compound that is also exhibit optical inactivity. So the answer to this question is option C. what I tell you is do as many as problems you can, try to do more questions, come up with different ideas to how to solve the questions. That will give you deeper understanding about the concept rather than studying the concept. Okay, so practice more, because practice makes a man perfect. So alkanes with the formula CnH2n plus 2, which means it starts with n is equal to 1 and goes like this: 1, 2, 3, 4, 5, 6. And also we know the simplest alkane, simplest hydrocarbon, that is methane, CH4, and then comes C2H6, C3H8, and goes on. Methane, ethane, propane, butane, pentane, hexane, heptane, octane, nonane, and decane. So talking about alkanes, we can't get rid of this isomerism part. We already talked a lot about isomerism in different types. Here in hydrocarbons chapter, we just have this straight chain isomers, structural isomers only. But if you want more about isomerism, I'll be linking the isomerism video in the description or in the I button. Please make use of it. Okay, so talking about isomerism, it is as simple as that, which will have same molecular formula but different structural formula, that is called structural isomerism. And for example, here I'm going to take hexane. Simplest hydrocarbons you can work on it. I'm just taking a 6 carbon system, which is hexane. So how can I write hexane in different ways? How can I write the different isomers of hexane? CH3, CH2, 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 CH3, that is N-hexane. Okay, so what is the molecular formula of hexane? That is C6, 2N plus 2, which makes it H14. So another way of writing it, by replacing one of those hydrogens with CH3. So CH2, CH2, CH3. So what is the molecular formula of this? Which is once again C6H14. And the name of this isomer is, the second position I am having methyl group. So 2 methyl, 5 carbons in the parent chain. So pentane. Correct? Then another way of writing hexane, 6 carbon system, can I place it in third carbon? Yes, I can. So which makes it as 3 methyl pentane. So don't think of it placing the fourth carbon, then it will become 2 methyl pentane once again, because we have to give the lowest number for the substituents. Okay, so what about combining these two? CH3, CH3, and CH3, and then CH3. The second and third position I am having methyl group. So 2,3 dimethyl. In the parent chain I am having 4 carbons, so which makes it butane. What if I am writing it as a tertiary carbon? CH3 on the same carbon. So total 4 and then CH2, CH3. What is the name of this? Which is 2,2 dimethyl. 4 carbons in the parent chain. So which makes it once again butane. Okay, so these are the isomers of the molecular formula C6H14. Okay, so once we know the isomers of straight chain isomers, let's move on to conformations. Conformations are again the spatial arrangement of our atoms which can be converted into another arrangement by a rotation. By rotation, we are changing it. The rotation must be a single bond, okay? We can't rotate the double bonded system, which is very, very strong. It's tend to break. So we are just rotating a single bond system. C bond C, which should be a single. What are you telling, ma'am? I got confused. Don't worry, I got you covered. Take an example of ethane. So ethane, the formula is CH3CH3. Carbon with three hydrogens. Once again, a carbon with 3 hydrogens. Okay. So how can I write it in case of Newman projection? This is a one carbon and the dot is in another one. So I'm writing the hydrogens for this carbon and hydrogens of another carbon. Okay, so here you can see the angle between the substituents, the hydrogens, are very, very less. This type of conformation are called eclipsed. Eclipsed. And what about another rotation, another 60-degree rotation of one of those carbons? So what will happen? I'm keeping this carbon as such. I'm just rotating the another carbon to 60 degree, which will give you the conformation like this. This conformation is called staggered. Comparing eclipsed and staggered, which is more stable? Always staggered is more stable than eclipsed. Why? Because there will be more strain on the angle of eclipsed conformation is very less than the staggered. Always there should be some space for each one of them, right? So staggered is more stable than the eclipsed conformation. Okay, so that's about isomers of alkanes. So what about their physical properties? There won't be much question asked about physical properties, but it's better to know. Talking about hydrocarbons, talking about alkanes, as the number of carbon atom increases, the boiling point also increases. Because the molecular weight will get increased, so the boiling point will also get increased. What about if I am having a branching, like we saw in 2,2 or 2,3, that more than that? What if I'm having more branches? So higher the branching, lesser will be the boiling point. Okay, which makes it occupies a small lesser area and the boiling point will get decreased. Say for example, if I am taking hexane compared it with 2,2 dimethyl butane, then boiling point of 2,2 dimethyl butane will be lesser than the hexane. Okay. If I am talking about melting point is always depend on the packing. So if that is closely packed, there is no much space between them, then the melting point will be higher. If there is more space, then the melting point will be lower. That is the whole idea of melting point, whatever the compound you can take. So the melting point increases with the number of carbon atoms, but increases which will also increase the melting point. When we move an even numbered alkane to next odd numbered alkane, the melting point will get increased. Okay, so let's move on to the more interesting part, that is preparation of alkane. If you are thorough with this hydrocarbons chapter, the 12th chapters like haloalkanes, alcohols will be a cakewalk to you. Okay, so please concentrate on your basics. Please concentrate on your reaction mechanisms, what type of substitution, additions or eliminations can happen. That is more important than memorizing those mechanisms. Okay, so coming back to the topic, preparation of alkanes. The simple preparation just we take first, that is from carboxylic acid. Carboxylic acid, we very well know the formula of carboxylic acid is RCOOH. Here I am taking it as a salt of carboxylic acid. Say for example RCOONA. I am going to dehydrate it using calcium oxide, and the temperature is 630 Kelvin. In the presence of base, this is happening. So I'll form RH with Na2CO3. Right? So just a substitution had happened over there. RH, which is an alkane, has been formed. What if I am taking RCOOK in aqueous? This reaction is very important. This is called Coles electrolysis. Anode part oxidation will happen and the cathode part reduction will happen. You can just go through those things, but end of the reaction you will get R with R. Okay, higher order alkanes can be prepared from this method, which is produced at anode part. That is very important. At anode, your end product, the desired product, has been produced. That is from carboxylic acid salts. As a second preparation, from alkyl halide. I told you, right? Haloalkanes chapter will be easy for you. From alkyl halide. Say for example, I am taking RX, treating it with 2 moles of Na. 2 Na means I have to use another RX or XR. You can write it in either way. Presence of dry ether. What can happen? You know that very well. RR will be formed along with that 2NaX. You can take any halogens to do this reaction and you'll be getting a high order alkane. So that what you can conclude is that preparing methane, it's not possible using this method. Okay, and if I am taking a different alkyl halide, what can happen? For example, I am taking RX with 2 moles of sodium with R-X. So the reaction conditions are same. If I'm taking a different alkynes, so I'll be ended up with R dash along with that 2NaX. But the yield will be very, very less. Why? Because there will be a chances of forming R as well or R dash as well. So which makes the yield is very less. This type of reaction is named as Woods reaction. It's one of those named reaction. We'll be revising this in Halo chapter as well. So please mark this as an important Woods reaction. Okay, let's move on. What if I want methane production. I want RH. What I have to do? In that case, you can treat Rx with palladium carbon, or you can go with nickel hydrogen, or you can go with copper zinc, zinc with HCl, zinc with NaOH, anything works. Basically with a catalyst, reduction catalyst, so that hydrogen will get added to produce RH. So what are the things I have told? Zinc with HCl, or zinc with NaOH, or you can take nickel with hydrogen, or copper with zinc. I'm just mentioning it as common, but you can use any one of these. Okay. Then the third preparation of alkanes involves from hydrogenation. What is hydrogenation? Addition of hydrogens. So you can add hydrogens from alkene or alkyne. Say for example, if you are taking RCH double bond CH2 and I'm adding the nickel catalyst along with hydrogen with the help of heat, so each one of those hydrogens will get added across the double bond. So in product will look like RCH2CH3. Similarly, you can go about with alkyne. The end product will be RCH double bond CH2. And once again, if you are giving hydrogens, it will take 4 moles of hydrogen, 4 hydrogens or 2 moles of H2 to proceed this reaction to get alkane. Okay, then the next preparation is that, don't worry, only the alkane preparation is more, and then alkene will be less, alkyne will be very, very less. The next preparation, that is from reduction of alcohol or carbonyl compounds, reduction method. So always you have to remember one thing: by reducing ROH, in this case I am using, it's depend on the alcohol I am taking and the catalyst as well. So here I am using ROH, I am generalized, but the reagent I am going to use is HI with red phosphorus. The reagent is very, 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 very important, guys, for this reduction. HI with red phosphorus, we will be dealing with this in myomolecules chapter as well, but in case of glucose and fructose, here also we are using it to make alkane. What about aldehyde? So in case of aldehyde, I am using again HI with red phosphorus, or you can use zinc amalgam with acid condition, or you can use hydrazine with basic condition. So zinc amalgam with acid condition, which refer to as Clemmensen reduction, and this part, if you are using hydrazine with a basic condition, then the reaction is referred to as Wolff-Krushner reduction. Okay, so I told you aldehyde chapter, we will see that. Here the formation of RCH3. What about if I am using carboxylic acid? Carboxylic acid with HI with red phosphorus, heating will give you RCH3. The next method, that is hydrolysis. Hydrolysis using Grignard reagent. So Grignard reagent, guys, who don't know, that is a versatile reagent. It is very, very important in synthetic organic chemistry. And this is an organometallic compound, which means that metal with organic compound, metal with alkyl groups. RMgX, that is a Grignard reagent. X can be of anything, any halo group. So I'm treating Grignard reagent with water. Of course, this is hydrolysis. Always remember, wherever the lysis word comes, that means for part, that means for cut, separate. Okay, hydrolysis means H2O will get separated as H plus and OH minus. You can remember it like that. So R will take up hydrogen and remaining OH will go to Mg. Then the last preparation is that from hydrolysis of carbide. So carbides, let's take Be2C. I'm treating it with water. This is an hydrolysis. So what can happen? CH4. How many carbons you are using, that much. Okay, irrespective of the carbon you are using as a carbide, you will get CH4. For example, if you are using Al4, C3, you will be ended up with CH4. And the reaction is that R with R dash or R, any R with R2CuLi, which is again an organometallic compound, presence of dry ether, which will produce R dash with R dash. So variant alkyl group. This synthesis is called Corey-House synthesis, and its reagent R2CuLi is known as Gilman's reagent. Okay. So Corey-House synthesis, Gold's electrolysis, Clemenson reduction, Wolff-Kishner reduction, and whatnot. These are the things we are seeing in Wood's reaction. These are the things we are seeing it in preparation of alkanes. So what I suggest you to do is, whenever you are starting an organic part, try to write all those named reactions aside. Because most of the questions in organic can be asked from named reactions. Okay. So whenever you are studying about the named reactions, write it separately in your notebook. Okay. So let's move on to the chemical reactions of alkanes. So alkanes, which is a saturated hydrocarbon. So which can undergo what kind of reaction? It can undergo substitution. Yes, it can. The substitution, as I told you, we already discussed very briefly about the type of substitutions in the last video. Here, in case of alkanes, let me take CH4 as a simple compound with Cl2. In the presence of UV or sunlight, it produces CH3Cl with HCl. How can I remember it? Yes. Here, what is the mechanism behind it? Why this is giving this product? This substitution, mostly you can remember wherever the substitution happens with HNO or sunlight or UV light, that happens with the mechanism of free radical substitution. So what is free radical? We discussed it. It is one of those intermediate that is having a unpaired electron in it. Right. So free radical It is highly reactive. So what is this mechanism of this kind of free radical substitution? This follows three processes you can take. The first process is chain initiation. Apart from other substitution reactions, this is a bit different. This is a bit different and interesting too. Chain initiation. So for that, I'm taking Cl. I just used Cl2, right? So I'm taking Cl, bond Cl. What happens? Homolectic cleavage happens, which means that each one of those atoms will take up one electron from the bond, since it is a covalent bond. And always, free radical mechanism must be written with a fish hook arrow, like this. It forms 2Cl radical. Okay. Then the step 2, that is chain propagation. Chain propagation. Propagation means continuation. What happens next? I took methane, so I'm writing it like this as a displayed formula. This methane, I told you free radicals are highly reactive. So one of those chlorine radical is reacting with methane. How? So it leaves like this to form a bond. So CH3 with the radical and HCl is formed. Is it a only way in the chain propagation? Why can't it be this CH3 radical reacts with another Cl? Yes, that can happen. So CH3 radical with another Cl radical come together to form our end product. But this is chain termination process. So I'm going to keep that below for now. Let's analyze what are the other ways of chain propagation can happen. Say for example, CH3 with the radical which formed in the chain propagation can react with ClCl to form CH3 Cl with Cl radical. Okay. So this kind of propagation means it never ends. Only if that ends, then that is a chain termination. Termination means ending, is it? So in case of initiation, the radicals are formed. In case of propagation, one of those products can form along with the radical formation. In the termination, all those radicals have come together to form and get settled with the product. But the main drawback of free radical reaction is that if that follows free radical mechanism, then the yield will be less. Yield is nothing but the end product, the desired end product. Why the yield is less? It's because of more the mix of products can be formed. Mix of product formation. Okay, so it can be mixed, like CH3 radical combines with Cl radical to form CH3Cl, and then you can find it out like CH3 radical combines again with another CH3 radical to form a higher alkane. That is also possible. Or Cl radicals again combine to form Cl2. That is also possible. So mix of products are forming, so the desired product yield will be very, very less. Okay. Then the next reaction is nitration. So nitration, I'm taking ethane, HNO3 in the presence of 423 to 673 Kelvin heat. One of those hydrogens are getting substituted by NO2. The remaining product will be water will be leaving. Along with that, an interesting part that can be CH3NO2 can be formed. So the substitution can lead to once again the more than one product. The third part, that is sulfonation. Here we are using H2SO4, but the problem is only from 6 carbon system it can undergo. It can undergo sulfonation. For example, C6H13 with hydrogen that may get replaced or substituted by SO3H. So C6H13 with SO3H. Then the next reaction, that is oxidation. Oxidation means we very well know addition of oxygen can happen. So here I am taking CH3CH3 in the presence of COO, CH3COO twice Mn. Where the oxidation happens, it will give acetic acid as a end product along with the elimination of H2O. What if I am taking a tertiary alkanes? So for example, like this. I am treating it with strong oxidizing agent K1O4, which will give CH3COH, CH3CH3. It is only possible for tertiary alkanes. What will happen if there is only one carbon map? For example, methane. Will it undergo oxidation? Of course, yes. Each one of them deserve a chance. So here I am treating it with carbon tube at high temperature and pressure conditions. It will form CH3OH. And if I am treating it with molybdenum oxide with the same temperature and pressure, I am getting a aldehyde along with water. So compare the reactions. Methane oxidation with copper tube, that will give you alcohol. Same methane with molybdenum oxide, that will give you aldehyde. So compare and study, that will be easier for you. Then this next part, that is isomerization. Isomerization, we already saw what is isomers are. For example, here I am taking butane, N-butane. As an isomer of N-butane, I am getting CH3CH3CH3 with the reagent that is more important. That is none other than anhydrous aluminium chloride with concentrated HCl. By the application of heat, I am getting isomers of the straight chain alkanes. Then comes pyrolysis. So pyrolysis, which is nothing but heat reactions. So CH3, CH2, CH3, I am treating it with high temperature. Always the pyrolysis wants high temperature. Any catalyst you can use to speed up the reaction. What will happen? Elimination is happening over there to give different alkenes. For example, 3 carbon as a propene, and you can get ethene as well, methane as well, and hydrogen as well. Okay. Then the last reaction, that is aromatization. We'll see what is aromatic compounds are, aromatization is formation of aromatic compound. I'm taking C6H14 as an alkane and treating it with chromic oxide or vanadium pentoxide or molybdenum oxide at high temperature and pressure, not so high, but 770 Kelvin, 10 to 12 atm pressure. Let's say I'm taking vanadium pentoxide. Once again, you can take chromic oxide or molybdenum oxide as well. I'm getting as benzene. It is one of those important preparation of benzene. Please note it down. That's it about alkanes. Now we are moving to alkenes. So alkenes, which will have double bond compound. Double bond is a p-pi bond once again, and which is sp2 hybridized, linear in structure, which can exhibit isomerism as geometrical isomerism. What is that? I told you in alkanes, conformations means the rotation of single bond. It can't rotate the double bond. Yes, that is true. In case of geometrical isomerism, we are taking a linear double bond system, but the twist is each carbon across the double bond should have different groups attached to it, like this. So if I am having a compound like this, it will not undergo geometrical isomerism. The two groups must be different. The two groups attached to one carbon must be different to exhibit geometrical isomerism, which is super important. Okay, some questions can be asked to find which of the following can exhibit geometrical isomerism. So please be careful with this part. Okay, so talking about isomerism, the two groups should be different, and if the same groups, for example H and H, CH3, CH3, Cl, Cl, so both the groups are on the same side, then this isomer is cis. Or if both the groups are on the opposite side, for example like this, then that is called trans. Okay, which are having same molecular formula and structures, but they are having different configurations. So due to that, what will happen? The trans isomer, which will not have a dipole moment, but the cis isomer can have the dipole moment, and the boiling point of cis isomer is more than that of trans isomers. If we need more about the geometrical isomerism, we have an already video on this. Please watch it. Let's dive into preparation of alkenes. The first preparation, that is dehydrohalogenation. What is dehydrohalogenation? D means eliminating the thing, hydro, hydrogen, halogenation for halogens. So which makes it an elimination process. It is a beta elimination. What is beta, ma'am? So beta part, that is where the substituent or the functional group is attached from that the near carbon to that carbon. For example, here I am taking CH3, CH2, Cl. So this is alpha carbon where the functional group or the substituent is attached, and this is beta. So beta elimination happens, and always remember, in case of elimination, use alcoholic KOH, not an aqueous. Always use alcoholic KOH. Alcoholic KOH undergoes elimination, aqueous undergoes substitution. So Cl and one of those hydrogens will get eliminated to give CH2, CH2 plus HCl. Similarly, dehydration, which means hydrogen can be removed, that is CH3, CH2OH if I am taking. Once again, this is a beta elimination. I am using concentrated sulfuric acid, OH, and one of those hydrogens will get removed to form a alkene. Third preparation, that is dehalogenation. Simply dehalogenation, which means halogens will be removed. Say for example, I am taking vicinal chloride. Vicinal means same groups attached on the adjacent carbon. Geminal is the same carbon. Zinc, which will end up with alkene along with the Cl. The next preparation, that is partial hydrogenation. This reaction we already saw in alkanes preparation from alkyne. If I am taking alkyne, I am doing the partial hydrogenation. Let's say I am using hydrogen with palladium, BaSO4, which will give you CH2. This reagent is for the preparation of cis alkene. Okay, here you can find cis and trans, but in case if you have taken R, C triple bond R with this reagent, you will be getting C double bond C, R, R. This is an example for cis alkane. So what if I want trans? Then change the reagent, sodium with liquid ammonia. I'm getting a trans alkene. So this reaction is called bridge reduction. Bridge reduction always give you trans alkene, and the former one which produced the cis alkene, the reagent is palladium hydrogen with barium sulfate. Here the barium sulfate is acting as a poisonous catalyst. Okay, then the final preparation, that is Gold's electrolysis. We already talked about Gold's electrolysis, where at anode we produced the alkane. Similarly, here we are taking 2 carbon system with a carboxylic acid salt. Electrolysis, it is producing CH2 double bond CH2 at anode. Now we are moving to physical properties of alkane. We have discussed it earlier, the hydrocarbons. The first 3 members of hydrocarbons of alkenes are gases, the next 14 are liquids, and the higher ones are solids. Higher the molecular mass, the compound will become more solid. And they show the regular increase in boiling points as the molecular weight increases and size increases. Every CH2 group added to the chain increases the boiling point by 20 to 30 Kelvin. So that is our physical properties. Now we are diving into chemical properties. Chemical properties of alkenes. The first thing, alkenes undergo electrophilic addition reactions. Electrophilic addition. We already talked about what is addition reactions and what are the mechanism it follows in types of reactions video. Here this is undergoing electrophilic addition, which means, for example, if I am taking CH3, CH double bond CH2, treating it with HBr, so HBr will get added to the double bond. So it will form a compound like this. Here you can get a question, ma'am, where Br will go, where hydrogen will go. So that is leads to the rule which is called Markovnikov's rule, which states that during electrophilic addition to alkene, the most stable product or the major product you can take, most stable product formed via most stable carbocation. That is our Markovnikov rule. I would like to define it in another way, which is you can remember it easily. That says about rich getting richer, which means that if I'm taking any HBr, HCl, HF, HI, so any electrophilic addition reagent, the hydrogen part, the positive part will go to more number of hydrogens. Let's say here hydrogen is positive, Br is negative. So hydrogen goes to where more number of hydrogens are there. Here the more number of hydrogens belongs to CH2, so hydrogen goes to CH2. Okay, or else you can remember it like negative adenine will join to the more substituted carbon. You can remember it in any way, but you should remember it. Okay, that is about Markovnikov's rule. What about if I am having peroxide with HBr, this kind of combo? I'm taking the same molecule, but here I'm taking peroxide along with HBr. In this combo, particularly HBr peroxide combo will lead to anti-Markovnikov rule. It's just opposite to Markovnikov's rule. So the product, major product, why I'm mentioning major product is because the another one which becomes minor. In case of first example, this product is minor, and in case of second example, this becomes major and the first product is minor. So the major product, that is the more stable carbocation, that is for Markovnikov rule. In case of peroxide with HBr combo, then it will lead to anti-Markovnikov rule, which is also known as Karash effect or peroxide effect. But that holds true only for this combo, HBr with peroxide combo. Okay, then what are the other chemical reactions alkene can give? I just listed out this in this way. Let's see one by one. The first one, which is hydrogenation. Hydrogenation, that will lead to give you hydrogen got substituted, got added to the double bond. So CH3, CH3. And this second one, X2 with CS2, which will lead to the addition of X on both the carbons. Both the carbons are across the double bond. And HX, as we discussed earlier, Markovnikov's rule. And the next one, H2SO4. Here you can see H and OSO3H. So that is our H plus and OSO3H. It is minus part. Then the point to be noted, that is cold KMNO4. Cold alkaline KMNO4, that leads to formation of glycol and this is a syn addition. Syn addition means both the groups are added on the same side. Syn addition, and if I'm using hard KMNO4, that will lead to the formation of CO2 with H2O. Okay, then peracid. Peracid means CH3COOH. Okay, so peracid with oxygen and silver, that will lead to the formation of epoxide, and then again followed by the hydrolysis, it will give you the anti-addition of OH groups. which will get added on the opposite side. Then comes ozonization, which lead to the formation of formaldehyde. Here I am having only 2 carbons. So formaldehyde has been formed. Whenever you are dealing with ozonolysis with double bonded system, the simple trick you can follow is that just put double bond O, break the double bond, put double bond O, write the product HCHO. Okay, if I'm having something like this, then again break the bond, put double bond O, write the product as CHO plus HCHO. Okay, that is ozonolysis. And then mercury salt with sodium borohydrate, which lead to the formation of alcohol, that is called Markovnikov addition with the reaction is called oxymercuration, demercuration. The next important reaction is that hydroboration followed by oxidation with BH3 or B2H6, whatever the dimer also they can give, with DHF as a solvent, which lead to the formation of alcohol, but here it is following anti-Markovnikov. Okay, so the next reagent, that is S2Cl2, which is giving us Cl, CH2 with sulfur. It is known as mustard gas. Okay, so that's it about the reactions, chemical reactions of alkene. Now we are moving to alkynes. So alkynes, we know that very well, which is a triple bonded system. For example, acetylene, and the hybridization is sp, so which makes it more electronegative, more S character, more electronegative. What would be the preparation of alkyne? So the first preparation, you can prepare it by hydrolysis. So let me write the alkene in the middle so that it will be easy to memorize. The first preparation, that is hydrolysis of carbides. So CaC2, treating it with water, which will lead to the formation of acetylene or any other, depend on the carbide, the triple bond will form. For example, if I am taking Mg2C3, then this won't be the product. The product is CH3 C triple bond CH for the hydrolysis. The second method of producing acetylene or triple bonded system is that dehydrohalogenation. Once again, that is a beta elimination process. I told you alcoholic KOH we have to use from CH2Br, CH2Br. Dehydrohalogenation happens with the elimination of 2 HBr molecules. Then, if I am taking CHBr2 with CHBr2, reacting it with zinc metal with heat, it is producing a triple bond system. That is, the reaction is called dehalogenation because halogens are getting removed. The next preparation is that from alkyl halide. For example, if I am taking HC triple bond CNA, the next very important preparation is that HC COOK. By seeing itself, you may guess the reaction, that is, yes, you are right, that is Goltz electrolysis. Okay, so these are the 5 important reactions to prepare alkynes. So what about its properties? What about its chemical reaction? So as you can see, Cl2 can react with acetylene to give CH2Cl, CH2Cl, and then if I'm adding HCl, that will get added up to 2 moles of HCl, means I'll get CH3CHCl2, which follows the addition process, and HOCl, once again 2 moles of HOCl, that will give you CHCl2, CHO, aldehyde is forming. H2SO4, I told you that separates as H plus and OSO3H minus, so that will get added. Mostly these alkanes are giving addition reactions. In this case, dilute H2SO4 with mercuric sulfate, it is giving us aldehyde. Oxidation happens, and then barium cyanide, addition of HCN, hot KMNO4. Point to be noted, hot KMNO4 in case of alkenes that gave CO2 with H2O. Here 2 CO2 has been produced, and in case of cold KMNO4, alkenes gave us alcohol with the syn addition. Here it is forming acid. And K2Cr2O7, once again oxidation happens to give acetic acid, and ozonolysis that leads to a formation of CHO. In case of ozonolysis, I told you in alkenes, break the bond and put double bond O. Here, just to break 2 bonds only, have 1 bond with the carbon and do the same. Put double bond O. You will get the product. That's it about alkynes. The next thing, very interesting thing, that is aromatic hydrocarbons. Aromatic. What is aroma? Aroma is a good smell. So these aromatic compounds are having very good smell, and which is very, very stable. For example, our benzene, our naphthalene. Okay, so these are some aromatic hydrocarbons. Here, while naming it, you have to consider one thing. In a benzene ring, if I am having a substituent, for example, I am having a substituent as CH3. From the substituent, I am numbering it 1, 2, 3, 4, 5, 6. Second and 6th position are ortho. Third and 5th position are called meta positions. And the 4th position is para. Okay, this thing you need to remember. Why I am saying this? Because if I want to name this, according to the functional group priority order, OH gets more priority. So the overall, without NO2, the compound is phenol. So in the ortho position, I am having nitro. So I should name it as orthonitrophenol. Okay. Similarly, you just try to name for this one. Okay. Let me know the name in the comment section. Okay. So aromaticity. What are the rules must be followed to find whether the compound is aromatic or not? The rules are very simple. Rule number 1, that is, the compound should be planar and ring, or you can take it as a closed system. Rule number 2, that is, the compound must have the complete delocalization of pi electrons. Delocalization of pi electrons. And most importantly, the number of electrons used in the delocalization must satisfy 4n plus 2 pi electron rule. Here n is equal to 0, 1, 2, 3 and so on. Okay. Say for example, if I am taking benzene, there are 6 electrons. So complete delocalization of pi electron, which means This bond goes here, this goes here, this goes here. So it just completed the ring. So it didn't stop anywhere, or it is having a conjugated pi system. Okay, what about number of pi electrons? Here this is having 6 pi electrons. Will that satisfy 4n plus 2 pi electron rule? Let's check. If I am substituting n is equal to 1, then I'm getting 6. So 6 electrons in benzene, so it satisfies 4n plus 2 pi electron rule, which also called as Huckel's rule. Any other examples can you tell me for aromatic compound? Yes, I can. For example, a system like this, which is closed and planar, that is having 2 electrons in it. It can undergo delocalization. It is having 2 electrons in it. So which means if I am substituting n is equal to 1, you will end up with getting 2. So which is also aromatic. You can try out with these compounds. You can include lone pair of electrons as well while doing this delocalization, because that can also involve in the electron delocalizations. These are some aromatic compounds. What if a compound that is ring, planar, but it is not satisfying 4n plus 2 pi electron rule, Huckel rule, but it is having other qualities, other criteria, complete delocalization, conjugated pi system, ring, planar and everything, but just it is not satisfying this rule, then that is considered as anti-aromatic compound. Anti-aromatic compound which should satisfy 4n pi rule. Then that is anti-aromatic. I'll be attaching a sheet which is aromatic, which is anti-aromatic, which is non-aromatic, and why that is so. I'll be attaching that sheet in the description. Please do check out. If you're getting any confusion in aromaticity, that sheet will be very, very helpful to you. Okay. Now let's move on to the preparation of benzene. The preparation of benzene, which is having 7 important reactions. The first one, I'm treating acetylene with red hot temperature, which will end up with benzene, and phenol with zinc dust will give you benzene. Benzene diazonium chloride with H3PO4. This is most important reaction. This reaction can be combined with other reactions to ask as a JEE Main and NEET questions as well, even in JEE Advanced. Okay, so the next one, COONA, sodium salt of benzoic acid, treated with NaOH to give benzene, and then hexane. N-hexane with chromic oxide and alumina. At higher temperatures, it will lead to the formation of benzene. And sulfonated benzene, upon hydrolysis, it is giving us benzene. And chlorobenzene, nickel with aluminium reduction, in the presence of base, that will lead to the formation of benzenes. Then we are going to look the properties of benzene, chemical properties of benzene. You can see benzene is a very reactive and versatile compound, but at the same time it is more stable. It undergoes many reactions. As you can see, benzene can take up chlorine to form chlorobenzene, take up nitro group to form nitrobenzene, sulfonation it can undergo, alkylation, acylation. So you can see these 5 are electrophilic substitution of benzene. So in case of electrophilic substitution, it follows a mechanism of formation of electrophile and attack of electrophile and formation of the products. But one thing should be clear. Here we are using AlCl3, which is a Lewis acid, which is having a vacant orbital in it. which facilitates the electrophile formation. Since it is having a vacant orbital, let's say I'm having Cl2, it will accept the electron so that Cl plus will be formed. So that acts as an electrophile to attack on benzene. Okay, so these are electrophilic substitution, and these two particularly called as Friedel-Crafts alkylation and acylation. Alkylation and acylation. Then other reactions with vanadium pentoxide, it is forming an anhydride, and following ozonolysis, it is giving us aldehyde, and treating it with chlorine with sunlight, it is forming as hexachlorohexane. 6 chlorines are getting substituted over here. What are the other reactions of benzene? Includes, it can undergo reduction using Branny nickel. That is most important reaction. Usually benzene will not undergo reduction unless or until the reaction is very strong. So in this case, we are using Branny nickel with hydrogen to form cyclohexane from benzene. So all of these reactions of benzene is super important. Okay. Then another important category in the types of reaction video I just told you, we'll see about this electrophilic substitution of benzene in detail in hydrocarbons. As I promised, here I'm going to tell you how this direction happens, whether that is going to ortho, whether that is going to para or meta, how it compound decides it. Okay, so how it influences the direction. The first thing is, if a compound, if a benzene ring is having a substituent which is electron donating group. What is electron donating group, ma'am? For example, if I am taking NH2, which is having a lone pair which can be donated, or NHR, OH, OCH3, NHCOCH3, or alkyl groups, methyl, ethyl, and all alkyl groups. So these are some electron donating groups. What that will do? How the electron donating affects the benzene influence of incoming electrophile group. So electrophile, which is an electron rich substance. Electrophile, which is an electron deficient one, which attacks the position where that is electron rich. Right. So due to the presence of these electron donating groups, as you can see in the resonance, in the structure, this ortho and para positions are having a electron rich place. So it leads to the incoming electrophile to ortho and para positions. So the incoming electrophile will attack ortho and para positions if a benzene ring is having a electron donating group. So what if that is having a electron withdrawing group? For example, nitro, cyano, aldehyde, or COR, or you can take carboxylic acid, COOR, SO3H. These are some electron withdrawing groups. It withdraws the electron from the benzene ring. So which leads to the electron rich position on meta side. You can see electron deficient site is produced on ortho and para. So comparatively, meta becomes electron rich. So which makes incoming electrophile to attack meta position. Okay, say for example, if I am having nitro and this is undergoing electrophilic substitution reaction, then the incoming electrophile is what? Nitro group, is it? So that will lead to the meta position to the existing substituent. What if I'm having a CH3 group on the benzene ring and I'm undergoing nitration? I'm doing nitration on it. What that will produce? Since CH3 group, that is an electron donating group, which leads to the formation of ortho-para substituent products okay. So comparing ortho and para, most of the cases para becomes more stable and major product than ortho. So that's it. F, Cl, Br and I. Mostly these four halogens we are talking about. Okay, so while naming those things, we have to use fluoro, chloro, bromo and iodine. Talking about the nature of CX bond, when it is forming a bond with alkyl group, CX bond, in that case, since this is more electronegative, halogens are more electronegative, it becomes polarized. It is pulling the electron cloud of carbon towards the halogens, which makes it polar compound, and the bond length increases from CF to Ci, which means CF is having shorter bond length, then comes CCl, then comes CBr, and then finally Ci. Why is it so? You can see iodine is bigger in size and less electronegative when we are compared to the fluorides. Then, talking about the physical properties of haloalkanes, it decreases with increase in branching. What decreases? Boiling point. We already discussed about this in previous organic chapters as well. The boiling point of isomeric haloalkanes decreases with increase in branching. Which means that, let's take a bromobutane 1, 2, 3, 4 and bromo group, and if I am writing the isomer of this bromobutane, I would like to write it as CH3, C with CH3 and then another CH3 with a Br. Methyl groups are attached as a branching, so which will have less boiling point than the straight chain. The boiling point of straight bromo, that is 375, and then the branched one is 346 kelvins. So which proves that as the branching increases, the boiling point will get decrease. Okay, so let's go into reactions. Let's go into our part, which is the first thing first, we have to prepare it. Preparation of haloalkanes. First, we are going to prepare it from alcohols. So if I want to prepare halo groups from alcohol, what reaction would be easier? That is substitution, is it? So let's take any alcohol or OH I'm taking. I'm treating it with anhydrous zinc chloride with HCl, which will give you RCl. Here you can see the tertiary will do wonders, which will react instantly, and then comes secondary and then primary. I'm talking about the timing. Why is it so important? This is one of the tests to discover what kind of alcohol is present, whether that is tertiary, secondary or primary. This test we'll again talk in next chapter, alcohols and alcohol, phenol and ether, but I'm saying you this test is called Lucas test. It is one of those preparations. Then if I'm taking a ROH, treating it with PCl5, as usual the substitution happens, RCl along with that POCl3 and HCl. In other terms, I can use SOCl2, which will give you again RCl, SO2 gas along with that HCl as a gaseous form. And you can use PBr3 to produce RBr, which I mean you can use any halogens to produce the corresponding halogens. Among these four, this method is more effective, which will give more yield. Why is it so? This is very important point, guys. Please note it down. Why is it so? Because these two byproducts are in gaseous state, which means that they will escape from the reaction mixture very easily. So remaining part is our yield. So the more yield, which is more convenient or best for the alcohol preparation part. Sorry, halogens preparation part from alcohols. The second type of preparation, that is from alkene. What you can do from alkene? Just you can do the addition, right? If I'm taking the simplest alkene, CH2, CH2, reacting with HX, what will I get? CH3, CH2X. We know very well about the Markovnikov's rule. We talked a lot about that in hydrocarbons chapter. You can check out that video as well, which will show you if I am having unsymmetrical double bond, unsymmetrical alkene, the HX addition, the negative part will join to the more substituted carbon, which means the major product becomes X and CH3. I told you the trick over there. H will go to the positive part, which will go to more the number of H. Rich is getting richer. And also we talked about the Karash effect, which means if I'm having same alkene, unsymmetrical alkene, but I'm using this combo HBr with any peroxide, H2O2 or any peroxide. This combo will do anti-Markovnikov, which means that this hydrogen will come and join here and Br will go and join to the CH2, which means negative part will go to less substituted carbon. That becomes your major product. I'm just writing here the major product, guys. So mostly the questions will be asked in the major product, is it? What will happen if I'm having a compound like this, which is symmetrical butene, 2-butene. Let's say I'm treating it with Br2, 2 halogens. So which means each one of those halogens will attack both the carbons on the double bond, which will create a product like this. You can say this is our meso compound. What is meso compound? If you are placing a mirror over here, if you are cutting it into 2 halves, both the sides will be same. Okay, so this is meso compound. How we can find the product will be meso? Whenever the reactant is in trans, whenever the reactant is trans alkene, which will lead to the meso product, meso attachment. And if I am having cis alkene, which means both the groups should be on the same side, then it will lead to racemic mixture instead of meso product, which will look something like this. And the mirror image of this, which is Br with H, H with Br, and then CH3, CH3 goes. So which is our racemic mixture? Racemic mixture, which is nothing but equal amount of D and L isomer. why we are getting this kind of racemic mixture for cis product, cis isomer, and why we are getting meso for trans. Have you ever think about it? Why? Because always you have to remember the addition of Br2 is anti-addition. What is that, ma'am? Anti-addition? Let me explain. So if I'm having a molecule like this, I'm adding Br2. So what will happen? It will take up one of those bromine to form an intermediate, brominium ion intermediate, which looks like this. And whatever the Br left is which will be there, since the downside is occupied, it will attack on the opposite side. It will attack on the opposite side, which makes it anti-addition. Okay, one from the bottom, if the bottom is occupied, it will attack on the opposite side, right? So which makes it to form BrH and BrH CH3. So if that is a cis product, if that is a cis butene. The second way of preparing, the third way of preparing haloalkanes, that is from silver salt. Let's say I'm taking COOAg reacting with Br2. The presence of sunlight, I have told you. This is whenever the sunlight or H nu comes, it will undergo free radical mechanism. Free radical mechanism, chain initiation, propagation, termination, we all know. Right? We have learnt about it in hydrocarbons and GOC chapters. So which will form RBr with CO2 and AgX. We do have a name for this reaction, which is called as Hunts-Stecker reaction. So if I want to tell you once again, this follows a free radical mechanism. First, it will form a radical out of Br2 and R radical. CO2 escapes as a gases, and Br radical and R radical combines finally in the chain termination step to form haloalkyls. But as I told you, the free radical mechanism, it will yield the low amount of yield when we are compared to other mechanisms. So that's why we are having some other method to prepare halogens. One of those important method is Wilkinson reaction. Which is only for iodides. R, X with X can be of anything. X can be of Cl or Br, of anything. But as an end product, it will give you iodide. For that, we are using sodium iodide and triacetone. So questions can be asked from this part. Which method is especially for iodides, haloiodides? Similarly, the next reaction that is super important, which have been asked in many years of papers, two directly, which is saying which method is used for the preparation of haloalkyl fluorides. That is none other than Schwarz reaction. Here I am using metal fluorides to produce alkyl fluoride. So that's it about the reactions of haloalkane preparation. Now we are going to properties. Before getting into properties, we have to understand one thing about the haloalkane, which is very reactive. Halogens are very reactive. But what would be the order of reactivity of halogens? The order of ease of displacement of these groups are not fixed, but it depends on the nature of R group present over there. And of course, the solvent affects a lot. If I am talking about the nucleophilicity, because halogens are rich in electrons, if I am talking about the nucleophilicity, is the order follows as I is more, then comes Br, then comes chlorine, then finally fluorine. This is the order of nucleophilicity, and we know SN1 and SN2 reaction mechanisms already. You can find that in types of reaction video. I'm attaching the link over here with mechanisms, with all other thing covered for SN1 and SN2 reactions. Okay, so to brief everything, SN1, that is following a carbocation formation, carbocation as an intermediate, and this is a unimolecular reaction, follows two-step mechanism. And in case of SN2, it is one-step mechanism, formation of a transition state. Concerted mechanism, formation of a transition state. That is a bimolecular reaction. Okay, so what is the reaction mechanism of halogens? These are the properties, chemical properties of halogens. When halogen is treated with dry ether with sodium, it is forming a high order alkanes, which is very important reaction, that is called Woods reaction. And alcoholic potassium cyanide, it is giving you the substitution reaction of formation of RCN. Ammonia, it is giving us amine. And with sodium acetylene, the acetylene part, so C triple bond CH is getting replaced with silver salt, OCOR, sodium alkyl thio, it is producing RSR. It's depend on the given R as well. Aqueous KOH, I told you guys, whenever you're seeing alcoholic KOH, that goes with elimination, and aqueous, it goes with substitution. So for substituting OH group, I'm using aqueous KOH. Okay, so other reactions are as follows. With magnesium and triether, which is a Williams Grignard reagent formation. Grignard reagent is nothing but RMGX. And then the point to be noted, very very important reaction with AgCN. Silver cyanide, it is producing RNC. If it is reacting with silver cyanide, it is producing NC, not CN. And if that is undergoing a reaction with KNO2, it's nothing but KNO2. KNO2, the oxygen is getting attached to the R group, and that is major product of this reaction. Oxygen is getting attached, so the product is RONO, and the minor product would be R nitro alkyl nitroalkane. But if I am treating it with silver nitrite, which is giving the major product as nitroalkane and the minor product as oxygen attached with the alkyl. Okay, I told you with alcoholic KOH, it gives us an elimination product, that is alkene. And this is also an important reaction, asked many times. Moist Ag2O and dry Ag2O. Dry Ag2O, that is producing as ether. with nickel and hydrogen, nickel as a catalyst, that is getting hydrogenated to form alkane, and with nickel it is giving us nickel halide and R halide. And finally with benzene it is producing, if I am using CH3X, that will lead us to produce toluene, which is nothing but the R group is directly attached to the phenyl tree. That's it. So these are the properties of haloalkanes. So let's solve some questions based on this, which was asked in previous papers as well. The first question: which reagent can't be used to prepare alkyl halide from alcohol? Which reagent can't be used to prepare alkyl halide from alcohol? The options are HCl with ZnCl2, PCl5, SOCl2 with pyridine, and D option is NaCl. We know that ZnCl2, I told you, that is Lucas reagent. PCl5, we can do that, and SOCl2, that is the best way to prepare haloalkanes. So the answer is none other than NaCl. And the next question is that CH3, CH3, CH double bond CH2 reacting with HBr and in the presence of H2O2. What is the major product? What is the major product? That is your question. So I told you this combo is for anti-Markovnikov. Which stays just opposite to Markovnikov rule. So which happens to be the hydrogen goes to more substituted carbon and Br goes to least substituted carbon. So which gives the product as CH3, CH, CH3, CH, H with CH2 Br. It is also called as Karash effect. Let's see one more question, which is asking CH3 with Br2 and HNO. It is giving us you the product. So what would be the product? That goes free radical mechanism. We know that. Take your time and tell me the product. You can pause the video and write down the name of the product in the comment. I can give you the hint, which includes free radical mechanism. So most stable free radical would be our major product. Cool? Okay. So the next question is that the compound which is having highest boiling point. The options are CH4, CH3Cl, CH3F and CH3OH. So these two are your homeworks. Write the answers in the comment. I'll check it whether you are right or not. Okay. So more the electronegativity, which makes the halo array to hold the electron pair of, which makes the partial double bond character over here like this. Okay, so which makes it partial double bond character. That's why I told you this is not undergoing SN2 or SN1. It is just undergoing SNAR substitution. Okay, so let's start with the preparation of haloarynes. The first preparation is from benzene diazonium salt, which is very important in synthetic organic chemistry, because this is very versatile compound which is used to prepare lot of compounds. How that will look like? Benzene diazonium salt will look like this. Benzene ring with nitrogen and Cl. Okay, so from this, how I can prepare halogen ring. So let me write that as C6H5N2Cl with CuCl and HCl, which will give us C6H5Cl with the elimination of N2 gas and Cl2. Those are the byproducts. This reaction is called Sand-Meyer reaction. Again, we will talk about this reaction in amines chapter. This is super important reaction, and the next one is equally important. That is C6H5N2Cl with CuHCl. Any halogens you can replace. You can put HBr also, which will give us C6H5Cl, that is chlorobenzene, along with N2 elimination. So this is called Gattermann reaction. These two reactions, guys, it is super important. How much ever important you want to mention, you can mention it that. Like we said in haloalkanes, I gave you Filkinstein reaction and Schwarz reaction. Those two are very important in case of preparation. Similarly here, Sand-Meyer and Gattermann. These are very important. Ma'am, you have told me chlorine and iodine, fluorine and bromine only. What about fluorines? How we can prepare fluorines? We can prepare fluorines from the same benzene diazonium salt with the special reagent, that is HBF4, hydrofluoric acid, which will give us C6H5Ef. This reaction is called Ball-Schiemann reaction. I told you this benzene diazonium chloride, each one of these reactions, each one of this synthesis is super important. The question can be asked in any part, because this is coming under alcohol, halo chapter also, and as well as amines chapter also. What about iodines? Yes, we can prepare it from benzene diazonium chloride. What not? Potassium iodide, presence of heat, is producing C6H5I. Okay. Only benzene diazonium will give halogens? No. We can prepare it using halogenation method also. This comes under electrophilic substitution. You remember in hydrocarbons chapter, I told you lot about hydrocarbon, how the electrophilic substitution happens, what are the groups directing where, and we have discussed pretty much all in electrophilic substitution. The simple substitution you can remember, that is C6H5 reacting with chlorine or bromine or iodine to give C6H5Cl, if that is reacting with Br2 with FeBr3. We should take any loose acid so that it can facilitate the electrophile formation. Br, and if I am treating it with iodine with HiO3, it is giving us C6H5I. And the next way of producing haloarenes, that is from silver salt. The third preparation, it is C6H5COOAg. You can use any halogen, it can be of Cl or Br, which will produce along with AgX plus CO2. And the fourth method, that is Rastrick process, which involves C6H6, that is benzene, I'm treating it with HCl in the presence of oxygen and CuCl2, which is giving us 2 moles of chlorobenzene along with H2O. This method, which is called the industrial preparation of chlorobenzene, which makes it super important, Rastick's process. Okay, so what about the properties of chemical properties of haloarenes? First thing first, always the nucleophilic substitution reaction. Nucleophilic substitution. I told you it will not undergo SN1 or SN2. It will undergo SNAR. So for doing SNAR, what that should have? It should have a strong electron withdrawing group in the para position to undergo substitution reaction. And you can take HCl to produce C. What if I'm not having any electron withdrawing group? I want only the reaction of haloarenes with other compounds. Then you have to have a drastic conditions like high temperature and pressure. Say for example, I'm having ARX. So I have to apply 623 Kelvin temperature and 300 atm pressure. As surrounding is 1 atm pressure, imagine 300 atm pressure, how much the pressure is high. Along with aqueous NaOH and HCl, which gives us OH, phenol. This is one of those preparation of phenol which is called Gauss process. And if I'm treating it with ammonia and copper oxide, again 60 atm pressure and 475 Kelvin temperature, it is giving us aniline. Similarly, if I'm treating this with copper cyanide with 475 Kelvin pressure, presence of pyridine as a catalyst, it is going to give you cyanobenzene. The presence of electron withdrawing groups such as nitro, cyanome at ortho position or para position, which will increase this kind of substitutions, nucleophilic substitutions, as we told earlier. But if you are using the drastic conditions of high temperature and pressure also, you can achieve it. The next thing, that is electrophilic aromatic substitution. Electrophilic aromatic substitutions. Let's say I'm taking halo or chloro, which will be the electrophile RCO, correct? And presence of Lewis acid to make it electrophile, which will produce ortho and para substituted product, which is like this and like this, ortho and para substituted product. Similarly, if I am treating it with Cl2 with FeCl3, it will again give ortho and para substituted dichloro products, because already I am having chlorine. It will give you dichloro product. Then if I am treating it with nitro as an electrophile, then again ortho and para substituted nitrochloro benzene. Then finally, if I want sulfonation, You can go with H2SO4, fuming H2SO4. If I'm having a reagent like this, CCl3 CHO with H2SO4. This will create a very interesting product which is called as DDT, that is having a very good application. It was having a very good application in agriculture field. It is producing DDT. What is that, ma'am? Which is 2,2 bis parachlorophenyl 1,1,1 trichloroethane. That is DDT. Okay, so we have seen the electrophilic aromatic substitutions, and the next thing is reaction with metal. Let's say I'm taking bromobenzene. I'm treating it with many metals. The first I would take sodium. Sodium with dry ether. Yes, that is right. What's reaction you have talking about? No, it's not Wood's reaction. Wood's reaction is only for alkanes. It's not for aryls. Then what is this? It's having the same reagent. Yes, this reaction is called fitting reaction. For example, it will produce as diphenyl or biphenyl, which means the higher order of aryls. This is called fitting reaction. Then, if I am treating it with sodium, it's CH3Cl and dry ether. You can see here I am having haloalkane also and arene also. So which means it will produce product like this. This reaction is Wood's fitting reaction. The combination of two. Then the next reaction, that is magnesium with THF, that is a solvent, tetrahydrofuran, which will produce in the Grignard reagent ArMgX. If I am treating it with nickel aluminium with NaOH, it is giving us benzene. So these are the reactions of haloarenes. Please do check it out, the uses also. I'm telling you, which is there in your book. Ferroin 12, which is one of the most common ferroins, which is in industrial use. And chloroform, you know that very well. Carbon tetrachloride, it is used as a fire extinguisher. And if we are inhaling more amount of this methylene chloride, which will cause the dizziness, nausea, numbness too. So the major use of chloroform is the production of the ferroin refrigerant. So uses also you have to give more importance. The questions can be asked from uses also. So before getting into preparation of alcohol, I would So alcohols, we are going to talk about alcohols, phenol and ether chapter. So first thing first, alcohol is a OH functional group. The boiling point, the alcohol shows increase in boiling point with increase in molecular weight among the distillate homologous series. And alcohols do have higher boiling point than the hydrocarbons of the same molecular weight. Okay, let's say if I'm taking pentanol and pentane, so alcohols will have higher boiling point. Why that is happening? Because of intermolecular hydrogen bonding. Alcohols will have higher boiling point than the corresponding hydrocarbons because of intermolecular hydrogen bonding. Right? Then if I'm talking about the solubility in water, if the molecular weight increases, the solubility of the water will get decreases. The lower alcohols are easily soluble. If there is a higher level alcohols, then it is not much soluble because of again the intermolecular hydrogen bonding between alcohol and the water molecules. Okay, so you can see, let's say I'm having an alcohol like this. This is water molecule and this is alcohol. I'm taking these two. So the bond formed between the oxygen and the hydrogen. So this, because of this hydrogen bonding, it makes it soluble in water. Okay, so let's move on to the preparation part. First, from the halo, it is giving us the aqueous means, as I told you, this is substitution. Substitution taking place from aldehydes. Upon reducing, it will give primary alcohol. From ketone, if I'm reducing it, it will give you the secondary alcohol. This is very, very important. We are going to see that in aldehydes chapters as well. From carboxylic acid, it will give you primary alcohols only upon reduction. Then esters, it will give you two types of alcohols depending on the R group we have taken. Then RCOCl, primary alcohol has been formed upon reduction, and here also it will give you the primary alcohol but 2 moles. With Grignard reagent with formaldehyde, here you go, the reaction proceeds to form a primary alcohol. The R group will get attached with the aldehyde. With ketone, it is forming as a tertiary alcohol because already in ketone we have 3 CH3 group. Again, this R group will get attached to the carbon, so it will form a tertiary alcohol. Then H2O addition. This is following Markovnikov rule in the acid medium. Hydroboration followed by oxidation. We saw that in hydrocarbons as well. So it is following anti-Markovnikov but syn addition. In CO with H2 is giving us again an alcohol. Then the important reaction, that is saponification reaction to form trihydroxypropane, which is also known as glycerol. Okay, so the reaction is very simple. We are taking ester, treating it with base, it will give you salt and alcohol. Then talking about the chemical properties of alcohol, with red phosphorus iodine, it is just forming hydrocarbons. With ammonia, it is forming aniline. Again treated with ammonia, secondary amine, or primary amine, then comes secondary amine, then comes tertiary amine. Okay, so excess of ammonia, the reaction proceeds forward. Then with iodine NaOH, it is forming iodoform. As I mentioned, this is very, very, very important reaction, iodoform or haloform reactions with alcohol. And the reducing agents like, oxidizing agents like PCC, PDC, it will give you aldehydes. Okay, these are some mild oxidizing agents that can give you only aldehyde. If I'm using strong oxidizing agent like K2Cr2O7 or permanganate, it will give you acids, carboxylic acids with the same number of carbons. If I'm taking 2 carbon in the alcohol form, I'll be getting 2 carbons only. Okay, with concentrated H2SO4, first H2SO4 will get attached. The hydrogen of H2SO4 will be taken over by the OH, leaves as H2O. Then the remaining reactions, H2SO4 in 410 Kelvin. The last reaction we saw 383 Kelvin. Here we are using 410 Kelvin. In that case, it will form ether instead of HSO4 addition. Substitution. H2SO4 in 433 Kelvin, it will form ethene. So this differentiation of temperature is very, very important. Then comes H2SO4 0 degree. Here you can see first it is forming the first step of the first reaction has been formed. Then Grignard reagent, it is forming alkene. Sodium, since it is acid in nature, alcohol. So alcohol is acidic in nature, so it is giving us the salt to prove the acidity. Then with pyridine and CH3COCl, it is giving us C2H5OCOCH3. Then, as I told you, the Lucas test, which is very, very important. This can be given as a clue point or can be asked as a strike question. The many types you can expect. Then phenols. Phenols, the naming is also important. Here the important phenols. Cresol, orthocresol, CH3 group with OH, that is cresol. OH, CH3 is ortho to OH, so that is orthocresol. Then catechol, that is 2 OH groups, dihydroxyphenol. Meta position means cresol, ortho position means catechol, and para position means quinol or hydroquinone. Hydroquinone means the structure will be like this. Okay, so the names are also important. Then the preparation of phenol, we saw this reaction in halo chapter as well. Downstream.
So alcohols, we are going to talk about alcohols, phenol and ether chapter. So first thing first, alcohol is a OH functional group. The boiling point, the alcohol shows increase in boiling point with increase in molecular weight among the distillate homologous series. And alcohols do have higher boiling point than the hydrocarbons of the same molecular weight. Okay, let's say if I'm taking pentanol and pentane, so alcohols will have higher boiling point. Why that is happening? Because of intermolecular hydrogen bonding. Alcohols will have higher boiling point than the corresponding hydrocarbons because of intermolecular hydrogen bonding. Right? Then if I'm talking about the solubility in water, if the molecular weight increases, the solubility of the water will get decreases. The lower alcohols are easily soluble. If it is a higher level alcohols, then it is not much soluble because of, again, the intermolecular hydrogen bonding between alcohol and the water molecules. Okay, so you can see, let's say I'm having an alcohol like this. This is water molecule and this is alcohol. I'm taking these two. So the bond formed between the oxygen and the hydrogen. So this, because of this hydrogen bonding, it makes it soluble in water. Okay, so let's move on to the preparation part. First, from the halo, it is giving us the upwards means, as I told you, this is substitution. Substitution taking place from aldehydes. Upon reducing, it will give primary alcohol. From ketone, if I'm reducing it, it will give you the secondary alcohol. This is very, very important. We are going to see that in aldehydes chapters as well. From carboxylic acid, it will give you primary alcohols only upon reduction. Then esters, it will give you two type of alcohols depending on the R group we have taken. Then RCOCl, primary alcohol has been formed on reduction, and here also it will give you the primary alcohol but 2 moles. With Grignard reagent with formaldehyde, here you go, the reaction proceeds to form a primary alcohol. The R group will get attached with the aldehyde. With ketone, it is forming as a tertiary alcohol because already in ketone we have 3 CH3 group. Again, this R group will get attached to the carbon, so it will form a tertiary alcohol. Then H2O addition. This is following Markovnikov rule in the acid medium. Hydroboration followed by oxidation. We saw that in hydrocarbons as well. So it is following anti-Markovnikov but syn addition. Then CO with H2 is giving us again an alcohol. Then the important reaction, that is saponification reaction to form trihydroxypropane, which is also known as glycerol. Okay, so the reaction is very simple. We are taking ester, treating it with base, it will give you salt and alcohol. Then talking about the chemical properties of alcohol, with red phosphorus iodine, it is just forming hydrocarbons. With ammonia, it is forming aniline. Again treated with ammonia, secondary amine, not aniline, primary amine, then comes secondary amine, then comes tertiary amine. Okay, so excess of ammonia, the reaction proceeds forward. Then with iodine NaOH, it is forming iodoform. As I mentioned, this is very, very, very important reaction, iodoform or haloform reactions with alcohol. And the reducing agents like, oxidizing agents like PCC, PDC, it will give you aldehydes. Okay, these are some mild oxidizing agents that can give you only aldehyde. If I'm using strong oxidizing agent like K2Cr2O7 or permanganate, it will give you acids, carboxylic acids, with the same number of carbons. If I'm taking 2 carbon in the alcohol form, I'll be getting 2 carbons only. Okay, with concentrated H2SO4, first H2SO4 will get attached. The hydrogen of H2SO4 will be taken over by the OH, leaves as H2O. Then the remaining reactions, H2SO4 in 410 Kelvin. The last reaction we saw 383 Kelvin. Here we are using 410 Kelvin. In that case, it will form ether instead of HSO4 addition, substitution. H2SO4 in 433 Kelvin, it will form ethene. So this differentiation of temperature is very, very important. Then comes H2SO4 0 degree. Here you can see first it is forming the first step of the first reaction has been formed. Then Grignard reagent, it is forming alkane. Sodium, since it is acid in nature, alcohol, so alcohol is acidic in nature, so it is giving us the salt to prove the acidity. Then with pyridine and CH3COCl, it is giving us C2H5OCOCH3. Then, as I told you, the Lucas test, which is very, very important, this can be given as a clue point or can be asked as a strike question. The many types you can expect. Then phenols. Phenols, the naming is also important. Here the important phenols. cresol, orthocresol, CH3 group with OH, that is cresol. OH, CH3 is ortho to OH, so that is orthocresol. Then catechol, that is two OH groups, dihydroxyphenol. Meta position means cresol, ortho position means catechol, and para position means quinol or hydroquinone. Hydroquinone means the structure will be like this. Okay, so the names are also important. Then the preparation of phenol, we saw this reaction in Halo chapter as well. Douse process, NaOH, 300 atm pressure. As I told you, this can't undergo any substitution reactions easily. That's why we are applying more pressure and temperature conditions. The process is called Douse process, and from diazonium salt, it is forming phenol in the presence of H2SO4, H2O. This question is also asked in the previous year question paper. With Grignard reaction, oxygen is forming as phenol with MgBr+. Then with benzene, with vanadium pentoxide, it is giving us phenol. And cumene process, this is cumene. It will be looking like this. Cumene process, cumene is reacted with oxygen and the peroxide to form. First, it will form cumene peroxide, followed by phenol and acetone. This reaction with the byproduct is totally important. This total process is important. This can be asked as a several questions. What is the intermediate? Cumene peroxide is intermediate. What is the byproduct? Okay. So what is the structure of the reactant? So many questions were asked already in previous year papers. Then chemical properties. With bromine water, this part is important. Listen. So with bromine water, it is forming as tribromophenol. Tribromophenol. With bromine with CS2, it is forming ortho and para substituted phenol, separately substituted. Okay. So this differentiation you must know. And phenol with neutral ferric chloride. This is a clue point. Phenol with neutral ferric chloride, it gives purple color. The question can be asked, X is treated with neutral ferric chloride, it is giving us a purple color. Means you have to understand that is phenol. Okay. Then phenol with dilute HNO3, again it will give ortho and para substituted product. And the question can be asked from here as well, picric acid. This is not having any carboxylic acid functional group, but still the name is picric acid. Okay. This is also known as 2,4,6 trinitrophenol. Okay. Then Scott-Bowman reaction. So Scott-Bowman means immediately this C6H5COCl benzoyl chloride should strike your mind. With phenol, that is giving us C6H5OCO C6H5. Because here I am having one phenyl group and another phenyl group is there in the reagent as well. Then another very, very important reaction, that is Reimer-Tiemann reaction. N number of questions can be asked from this reaction. Okay. Phenol is treated with chloroform NaOH to give ortho and para substituted product. The major product is orthosalicylaldehyde because of the hydrogen bonding. You can see the mechanism over here. CHCl3 treated with KOH to form carbenes. This is carbene. We very well know about the intermediate, is it? So carbene, this is getting attached. This is what the reaction flow is. The question can be asked from carbene as well. Okay, what is the intermediate formed over there? Then salicylaldehyde has been formed. Then CCl4NaOH is forming salicylic acid. Then Gold's reaction, phenol with NaOH CO2. Gold's reaction means there will be CO2. So CO2, 400 degrees, 400 Kelvin, 427 atm. It is forming again salicylaldehyde with CrO2Cl2. It is forming parabenzoquinone. Mistake had happened over there. So parabenzoquinone as a product. Then phenol with benzene diazonium chloride, it is forming as orange azo dye. So this is also a very important clue point. Then ethers. Ethers, the naming is important and some preparation properties. Very simple, very short. Phenol, alcohol with H2SO4, 413 Kelvin, it is giving us ether. We saw this reaction just now. Then the next preparation, that is Williamson synthesis, where I'm taking alkyl halide with RONA. This is acting as a base to give ethers. So RO minus will attack the carbocation part. This follows SN2 mechanism to give ethers. The properties of ether, as you can see, with HI it is forming Ri. With excess of HI it is forming 2Ri with H2O. So these two differentiation you must understand. Then anisole, that is aromatic ether. With Br2 acetic acid, it is forming para and auto substituted product. With CH3Cl, AlCl3, once again that is in Friedel-Crafts reaction, right, to give para substituted product. So that is about ether group. Next we are moving on to carbonyl compounds chapter. So in carbonyl compounds chapter we have different carbonyl compounds like aldehyde, ketone and carboxylic acids we are going to see. So first aldehydes. So aldehydes, as we all know, which is having CHO functional group, ketone, that is RCOR. So this can exhibit metamerism. Okay, so be careful with that guy. Then if I'm talking about the preparation part, the naming part, just revise. The name of nomenclature questions can also be asked. We also included the nomenclature here, is it? So nomenclature part is also important in case of carbonyl compounds. Here you can see the preparation part, the first preparation with oxidation of alcohol. I'm giving you the trick. If I'm taking primary alcohol, 1 second. Taking primary alcohol, upon oxidation that will give aldehyde, and further oxidation that will give carboxylic acid. Similarly, if I'm taking secondary alcohol, upon mild oxidation that will give you ketones, and further oxidation that will also give carboxylic acid with less number of carbons. Okay, so that is an important part in carbonyl compounds chapter. Okay, so you must know what are those oxidizing agent, which is mild oxidizing agent, which is strong oxidizing agent. Mostly they will give the strong oxidizing agent as KMnO4 and K2Cr2O7, sometimes osmium oxide. Okay, so this particular reagent, Jones reagent, is for the conversion of secondary alcohol only, secondary alcohol to ketone. Okay, in case of primary alcohol, that will immediately form COOH, carboxylic acid. So we are particularly taking this for secondary alcohol only. Then hydrogenation with acid chloride. This is a very important named reaction, that is Rosenman reduction. So palladium is acting as a catalyst and barium sulfate is poisonous catalyst. From RCOCl it is forming RCHO. Then distillation, upon the release of CO2 it is forming aldehydes, and from alkene oxo process to form aldehyde with 1 carbon extra because of carbon monoxide we have added. Then Gattermann-Gove synthesis, where we are taking benzene with carbon monoxide and HCl, which will give you aldehyde. Gattermann aldehyde synthesis, where I'm using HCl with HCl, that will give you immediately aldehyde. Then MnO2, that can also leave you with aldehydes. So these are some important reactions. The major important reaction is Stephan reaction. So Stephan, you can remember it, SNCl2, because there is another reaction which involves SNCl4. So here SNCl2 with RCN, that is giving us ammonia with aldehyde. And with Grignard reagent with CN, which will give you ketones. Nucleophilic addition. So nucleophilic addition, it happens in the around the acidic medium, pH of 3.5. Usually the very important stuff in nucleophilic addition is the 2,4 DNP reaction. Okay, this will be given as the clue point. The 2,4 DNP is giving positive, which means this free CO group is there. Okay, so that is an important clue point over here. Then comes our HCN. With HCN, which is forming cyanohydrine, OH group, along with that CN. Then NaHSO4, Grignard reagent, once again this forming alcohol. And as you can see, I have listed the groups over here. NH2 with any group, another NH2, OH or 2,4 DNP or any other group, which will lead to the formation of the structure like this, hydrozones. Then oxidation reaction, Tollens and Fellings reagent. What is Tollens reagent? Tollens reagent is ammoniacal silver nitrate, and Fellings solution is a mix of filling A and filling B, which is nothing but copper sulfate and sodium potassium tartrate. So with this, it will give you positive, means that is having aldehyde group in it. Okay, so as you can see, tolerance reagent, the positive result is showing of the silver mirror. On worst case, that will give you the black precipitate. With filling solution, that will give you the red precipitate because of the formation of CO2O. Okay, both the reactions, it's an oxidation reaction. As you can see, it is forming RCOO minus. Then the next one, so the reduction part, upon reducing ketone, it will give you secondary alcohol. Upon reducing aldehyde, it will give you primary alcohol. We already saw that. Clemmensen reduction and Wolff-Kishner, this is happening in the acidic medium. This is for acid sensitive groups. Okay, then polymerization. This part is important because it is forming a paraldehyde, metaldehyde, with depend on the number of aldehydes I'm taking. Then the most important reaction in this chapter, that is aldol condensation. Aldol condensation means that should be a alpha hydrogen in the aldehyde. So we should be forming a aldol at the end of the process. That's why we are calling it aldol condensation. First, it will form beta hydroxy aldehyde. So how the mechanism happens? The first step is formation of carbon ion, and then carbon ion attack with another aldehyde to form a reagent like this. Then it will form aldol. Alcohol with the aldehyde, that's why aldol. So upon treating it further, it will form alpha beta unsaturated aldehyde. The next one, that is Cannizzaro reaction, it is also equally important. Here the condition is there should not be any alpha hydrogen. For example, here you can take benzaldehyde. It is undergoing the reaction with basic medium to form. This is nothing but a disproportionation reaction. Cannizzaro reaction is a disproportionation reaction. What is that? It is the same compound will get oxidized and then reduced. So aldehyde, upon oxidation, that will give you carboxylic acid. Upon reduction, it will give you alcohols. Okay. Then the mechanism, if you want, you can refer it to. I'm just attaching it. This one following a dianion followed by the addition of another aldehyde. If I'm taking two different aldehydes, then it would follow cross-Cannizzaro reaction. Then condensation of acetone. Acetone just condenses to form a mesylene and phenolone, just a release of water. Hydrolysis of alkyl cyanides, just you can see H and OH will get attached. Upon hydrolysis of cyanide, it will give you carboxylic acids at the end. First, that will give you amines, followed by that, it will give you carboxylic acids. Then, we are moving on to carboxylic acid part. So what are the derivatives we have for carboxylic acid? That is acid chloride, anhydrides, amines, and esters, right? So you can see the usual preparation. This we know from secondary alcohol also we know. Then haloform reaction, we already talked about this. And what are the compounds will give positive to the haloform reaction with carbonyl compound? That is, this should have a CH3 group attached with the functional group, directly attached with the functional group. So as you can see, this will give you positive. This will give you positive, and this will not give you positive to the haloform reaction. So if they are mentioning that this is giving positive to the haloform reaction, then you have to assume that this is having the CH3 group directly attached with the functional group. So that is the clue point it is giving. So then the terminal trihalogen reactions, all three OH group will get attached over there, which is unstable. So it is forming a releasing H2O to form carboxylic acid, and with CO2 with Grignard reagent, it can give you carboxylic acids. Ester hydrolysis, hydrolyzing esters, it will give acid, carboxylic acid and alcohol. This is very, very important, very basic also. Action of heat, what will happen? CO2 will get evaporated, then dicarboxylic acid will give you monocarboxylic acid. Then moving on to the post reaction, Again, alkene is giving us carboxylic acid group. So this reaction, we already saw that in hydrocarbons part, the oxidation happens with potassium permanganate. This is a syn attack. Then the chemical properties of carboxylic acid. Since there is an acid, it can be attacked by the base or metal to form its salts. The important step over here is that with carboxylic acid, if I'm treating it with sodium carbonate or sodium bicarbonate, it will release carbon dioxide. That carbon dioxide is from the sodium carbonate or bicarbonate, not from COOH. So the isotopic kind of question can be asked from this part. Then esterification, we very well know, and which will favor the primary, then comes secondary, then comes tertiary. Then the interesting question here, you can expect that this formic acid will undergo the process of dehydration or not. It will not undergo because of the form. It will not form the anhydride. It will directly form CO2 and H2O. So the answer is no. Then RCOOH with ammonia, it is forming amines at the end. With AlCl2, Al2O3, it is forming RCN. So they have listed some reducing agents and oxidizing agents as well. These are some reactions which carboxylic acid is undergoing. Among this, the ketene process is also important, and diisomethane is also important, which questions have been asked in the previous year papers. The named reaction, Suskimet reaction, which involves N3H. Okay, it's not ammonia, N3H. So it will give you amines and CO2 and N2. And acid synthesis, it is a homologation formation. What is that? One extra carbon will be added over there in the product. So RCOOH is reacting to form RCH2COOH. Then Helen-Ohal-Zelinsky reaction, HVZ reaction, which is having the alpha hydrogens, like we said for aldol. With red phosphorus and Cl2, it is forming alpha halocarboxylic acid. This is important because there are so many reactions we have seen that is getting attached with the functional group, right? Here that is adding with the alpha hydrogen. Alpha hydrogen is getting substituted when it's substituted by our halo group. Then we came to the chapter amines. So it is a very small chapter, but at the same time you can expect some questions. Very important chapter as well. So let's quickly go through this chapter. The first thing first, amines, which is having NH2 functional group. The question can be asked from the basicity also, and also from the reactions. The reaction involves the first preparation is that alpha Hofmann alkylation. We already saw this reaction. Upon adding excess of ammonia, it will give you primary, secondary, tertiary, and quaternary amines as well. Then the second important reaction, that is Gabriel thalamide synthesis. This is not for aromatic amine. This will give you the primary amines, alkyl primary amines. Then Hofmann bromamide. This is an important named reaction. 5-step process it involves. This is also gives primary amines. The reagent are Br2KOH. From amide, this is giving you amines. You can see one carbon less in the product. So we have seen 1, 2, 3 reactions where one carbon extra in the product. Here, this particular reaction which is having one carbon less in the product. Then the reduction part. Reduction means nothing but the hydrogen addition. From amides, it will give you amines. From cyanides, it will give you amines. And for the preparation of secondary amines, you can take isocyanide to give secondary amines. Nitro, of course, that will give you amines. This is very, very important. Nitro is getting reduced to give amines. Then the properties of amines. The basic nature, before that, usually two types of question can be asked, in aqueous and in solid or powder state. So aqueous means tertiary will be more basic. Solid means primary. So secondary will be more basic. Solid means tertiary will be more basic. So thus you have to remember. Then the reactions involving basicity nature of amines. As you can see, the lone pairs of amine is donating. The lone pair of nitrogen is getting donated to other groups. With nitrous acid, RNH2 is giving us ROH. With aniline, it is giving benzene diazonium salt. Benzene diazonium salt will not be formed from the aliphatic amines because of lack of resonance. Okay, if that is reacting with secondary amine also, it will give you yellow oil liquid. These are the distinguishing tests for aromatic and aliphatic, and as well as the primary, secondary, and tertiary amines. Then acylation reaction. Secondary amine is giving you tertiary amines, and RNH2 is giving you RNHCOR. Then with Grignard reagent, it will give you RH and the alkanes. Then carbamide reaction, which is equally important, with chloroform KOH, it will give you isocyanate. Mustard oil reaction with CS2, this is forming isothiocyanate RCNS. So remember the formula, guys, which is important. Then, as I told you, the distinguishing aromatic and primary, secondary, and tertiary. This reaction with nitrous acid. Nitrous acid is nothing but we are treating nitric acid with base. So these type of transformations you can expect. Then finally, benzene disodium chloride, Sandmeyer reaction, Gattermann reaction, Ball-Steven reactions. These are important. And one more reaction I wanted to tell you, that is H3PO2. This will give you benzene. So this is the question asked 2 years back. So please be careful with that. Then beta naphthalate, it will give you the dyes. These are some dyeing reactions for benzene disodium chloride. These are some important reactions. Benzene disodium chloride has n number of applications. These are some important. Carbohydrates are defined as the polyhydroxyaldehydes or ketones, or the substances that generally give these on hydrolysis. So basically, either this can be of polyhydroxyaldehydes or ketones, or upon hydrolysis, this will give aldehydes and ketones. And also, it contains at least one chiral carbon. What is chiral carbon? The carbon which is attached with 4 different groups. Hence, it becomes optically active. Right. So the general formula of carbohydrates is CXH2OY. X and Y can be of numbers. It starts from 3, 4, 5, 6, like that. Okay. But if you're asking me, only carbohydrates lies with this formula, I would say no. But the more appropriate word is that mostly, because this formula holds true for acetic acid as well. Okay, let's get back to the subject. Carbohydrates are classified into based on 3 types. The first type is based on molecular size. Here, carbohydrates have 3 types, that is monosaccharides, disaccharides, and polysaccharides. We are going to study in detail about this type in a while. Let me take you through the other 2 categories as well. Based on taste, it can be of sugars and non-sugars. And based on their reducing property, this can be of reducing and non-reducing sugars. What it reduces? And you are saying reducing property, what it reduces? Carbohydrates which can reduce Tollens reagent. What is Tollens reagent? Ammoniacal silver nitrate. And filling solution. Those are called reducing sugars. Okay, if a carbohydrate reduces those 2 reagents, then that is reducing sugar, and which can't reduce those reagents, then that would be non-reducing sugars. For example, glucose and fructose both are reducing sugars, but sucrose is non-reducing sugar. Reducing sugars contain either alpha-hydroxyaldehyde or ketone, or they contain a cyclic hemiacetal or hemiketal structures, or maybe they are equilibrium with that structure, so that it reduces Tollens and Fellings reagent. Basically, it should have a aldehyde or alpha-hydroxyaldehyde or free ketones to get reduced. Okay, on to the chemical reactions of glucose. Glucose is a monosaccharide. Where we are getting glucose? The mother of glucose, where we can prepare glucose, is from cane sugar or sucrose. The formula of sucrose is C12H22O11. Upon hydrolyzing this cane sugar or sucrose, we are getting 2 same molecular formula compound, that is glucose and fructose. Both the names are different, but the molecular formula is same, C6H12O6. and where we can get glucose. It occurs in ripened grapes, honey, and most of the sweet fruits. Glucose is known as a dextrose because it occurs in nature, as also there is an optically active dextrorotatory isomer. Let's see about the chemical properties of glucose. The first reaction is with acetyl chloride, CH3COCl. Glucose with acetyl chloride in the presence of zinc chloride, it forms glucose pentaacetate. How will that look like? Glucose, which will have a aldehyde structure. We are going to do the structural elucidation also. And then OCCH3 4 times, and then CH2OOCCH3. That is glucose pentaacetate. Along with that, so alcohols, we are going to talk about alcohols, phenol and ether chapter. So first thing first, alcohol is a OH functional group. The boiling point, the alcohol shows increase in boiling point with increase in molecular weight among the distillate homologous series. And alcohols do have higher boiling point than the hydrocarbons of the same molecular weight. Okay, let's say if I'm taking pentanol and pentane, so alcohols will have higher boiling point. Why that is happening? Because of intermolecular hydrogen bonding. Alcohols will have higher boiling point than the corresponding hydrocarbons because of glucose with acetyl chloride in the presence of zinc chloride, it forms glucose pentaacetate. How will that look like? Glucose, which will have a aldehyde structure. We are going to do the structural elucidation also. And then OCCH3 4 times, and then CH2OOCCH3. That is glucose pentaacetate. Along with that, HCl will be produced. This reaction demonstrates the presence of hydroxyl groups, because wherever the hydroxyl groups are there, this aceto group will get attacked. This group will get attacked the OH position to form a acetate structure. So in total, I'm having 4 acetate group formed, which 4 plus 1, 5. So which means that 5 hydroxy groups were there in glucose. Okay. Next reaction is that treatment with PCl5. Reacting with PCl5, glucose gives pentachloroglucose. The structure goes like this: CHO with CHCl 5 times with CH2Cl. Technically, it should be 4 times. Yes. So I just segregated the primary and secondary alcohols. Okay, this is pentachloroglucose. Along with that, it is forming POCl3 and HCl. We have seen the reaction with PCl5 with hydroxy groups in the alcohol chapter, right? It's just replacing the OH group with Cl. The same thing happens here also. It confirms the presence of hydroxyl groups. Total, how many hydroxyl groups are there in glucose? 5. Okay. The next reaction, that is reduction reaction. When glucose is treated with sodium amalgam and water, it forms sorbitol. The structure is given over here, sorbitol. This reaction shows that glucose can be reduced at its aldehyde group. You can see in previous reactions I just mentioned the CHO group, aldehyde group. But here, that aldehyde group got reduced to CH2OH, which confirms the presence of aldehyde group present in the glucose. Then oxidation. Upon oxidizing glucose with bromine water, These two are very important, guys. So note it down. With bromine water, glucose forms gluconic acid. And with nitric acid, it produces saccharic acid. I'm telling you the formula as well. For gluconic acid, CH2OH with CHOH 4 times and then COOH. That is formed when glucose is treated with bromine water. Gluconic acid is formed. And saccharic acid. Saccharic acid formula is COOH with CHOH 4 times COOH. Most of the students get confused in this reaction. Please make a note of it. Saccharic acid, which is having 2 COOH, because it is with nitric acid, it is doing an additional oxidation. But in case of bromine water, primary hydroxy group still remains the same, and aldehyde got oxidized to COOH. Okay, and formation of these acid proves that the presence of both aldehyde and primary alcohol groups are there in the glucose. Then formation of glucosone. We have seen this ozone formation in aldehyde chapter. What we have seen, when the presence of carbonyl groups, this phenylhydrazine structure is C6H5NHNH2. We have seen hydrazine simply also, right? And 2,4 DMP. So those are comes under the same category. What happens over here? So with aldehyde group is just react like this: CH double bond N NH C6H5. Water molecules will get eliminated, and here also N NH C6H5 and then CHOH 3 times, along with that CH2OH. This is glucosone, which has a characteristic yellow needle-shaped crystals formation. This is a crucial identification test for glucose. Okay. Other than this, we have some structural insights as well. The straight chain structure of glucose explains most of the properties. The important test for straight chain is that HA with rest phosphorus. Glucose gives a 6-carbon system. That is hexane, N-hexane formation, which gives glucose is having a 6-carbon system. But these have failed to explain these 3 important observations. The first observation is that no reaction with 2,4 DMP and sodium bisulfate. Although that is holds true for those straight chain, but these tests are fails. And then no reaction of its pentaacetate with hydroxylamine, NH2OH, and existence of alpha and beta forms. Okay, so these 3 are important part. So what is alpha and beta forms of glucose? Before that, through these observations, what we have found is that glucose is not having a straight chain thing, it is having a cyclic structure. And also the equilibrium exists with the open chain form. Right, as you can see, D plus glucose is there, alpha and beta forms are in the equilibrium. You can clearly see the difference of alpha and beta form with OH groups. Okay, let's move on. And glucose is a 6-membered ring containing an oxygen atom in the pyranose form. Okay, I'll show you the glucose structure as well in a while. These properties are very similar to fructose as well. Okay, but fructose is having a 5-membered structure because the structure is differ in this point. Fructose contains keto group, but glucose is having aldehyde group in it. Okay, these are the key difference between fructose and glucose. You can see the fructose structure as well. Fructose is furanose structure but glucose is pyranose structure, like this. Please work on this structure. This is very, very important. At what point the OH groups are differently attached, that is important. Okay, then there is a term called mutarotation. What is the definition of that? What does it mean? When these two anomeric forms, like alpha and beta, are separately dissolved in water, they undergo a specific rotation change till it becomes constant after some time. What is specific rotation? We know that optically active compound, when we are passing it through the plain polarized light, there will be a rotation caused by it. It can be of clockwise or it can be of anti-clockwise. Those values are noted. Those are the specific rotation of that particular compound. Here you can take, from taking alpha D glucose, convert into the beta D glucose in aqueous solution and reaching a equilibrium point, but the specific rotation changes from 112 degree to plus 19 degrees. Okay, so this kind of rotation is kind of changes is called mutarotation. And another important term in carbohydrates, that is anomers. The question can be asked from this part: what is anomer? Which of the following is anomer? That kind of question you can expect. Anomer is very simple. It refers to a pair of stereoisomers which differ in configuration only around C1. That is more important. Only around C1 position, that is called as anomeric carbon or glycosidic carbon. This explains the existence of alpha and beta forms of glucose. Okay, as you can see, I'm showing the glucose structure once again. The OH group, H and OH, differs in C1 position. That is changing in case of alpha and beta glucose. Okay, these are glucose fructose are monosaccharides, right? It can't be hydrolyzed further. It is a hydrolyzed form. It is, we are getting it from sucrose, that is a disaccharide. The next concept we are going to see, that is disaccharides. Disaccharides are nothing but, when we are hydrolyzing it, it should give two sugars, two molecules of carbohydrates. They are disaccharides. For example, sucrose. It gives glucose and fructose. It is a non-reducing sugar. Note it down. Each and every point, note it down. It is a non-reducing sugar. Maltose, which is having the same molecular formula as sucrose, but it is a reducing sugar. And lactose, formula is same, but it is also a reducing sugar. Sucrose is non-reducing, note it down. Okay, what about polysaccharides? Polysaccharides are the one which can give three or more than three molecules upon hydrolysis. For example, starch. Starch is the most significant polysaccharide compound. It is an energy source for humans, that we know. And what are the key characteristics of starch is that it consists of two main components, amylose and amylopectin. Amylose and amylopectin. Amylose is a straight chain that is having alpha 1,4 glycosidic bonds. Alpha 1,4 glycosidic bonds between glucose. But in case of amylopectin, it is a more complex structure, but point to be noted here is alpha 1,4 glycosidic bonds in the main chain and 1,6 glycosidic bond at the branching chain. Okay, so these points just note it down, which are very, very important. Just erasing it so that you can view that clearly. But these are very important. The questions can be asked from this. That's why I'm telling you these are important. When we eat starchy foods like rice, chapati, any form of rotis, bread, bun, you eat pav bhaji, everything. Any kind of starchy food we eat, our body begins to break down it immediately. How it does, how the process works is that first starch is becoming dextrine and then it goes as maltose. See, the formula changes dextrine to maltose and then it got separated to glucose. The sequence. So how we can find the presence of starch? That is also an important question. The property of the starch is its reaction with iodine. With iodine, it will give characteristic blue color. Okay, that tincture solution, tincture of iodine, is nothing but you can check that color it will produce. It serves as this test is a key identification test for presence of starch. Starch does not reduce swellings and tolerance reagent, but its reducing groups are involved in glycosidic bonds. That's why this is not reducing the reagents. Okay, the second important polysaccharide is cellulose. It is different from starch. Where we saw that word cellulose, it's from plants, isn't it? So it is a structural framework of plant cell walls and is remarkably abundant. It is having 90 to 95% of cotton and 45 to 50% of wood. The structure involves beta-D-glucose unit connected by beta 1,4 glycosidic linkages. You see 1,4, 1 from one position to fourth position, and then first position to fourth position. This is what they meant by 1,4 glycosidic linkage. Okay, so these are beta structures. You can see this is a beta glucose structure, and that's why we are saying beta 1,4 glycosidic link. Okay, then glycogen. Glycogen is often called as animal starch, which serves as a storage form of glucose in animals. We can find this in livers, muscles, and brain as well. It is having a structure similar to amylopectin, but it is having amylopectin. I told you that is a complex structure, but still this is branched in case of glycogen. Next, we are going to talk about proteins and amino acids. Proteins are the complex molecules composed of amino acids linked through peptide bonds. What is that peptide bond? Let's say you are having carboxylic group and amine group, COOH and NH2. What will happen? One hydrogen from here. What will happen? OH from here and hydrogen from here gets removed, remaining CONH. That is what the peptide bond is. It is an amino acid. The breakup of protein is that peptide amino acids are linked through peptide bonds. Okay, and these amino acids share a common structure but differ in their side chains. That's what more important. Amino acids are classified into several categories. Let's see few important categories. Before that, these are colorless, non-volatile solids with high melting point and highly soluble in neutral solutions. And most important question can be asked is that except glycine, remember the name, glycine, all other amino acids are optical isomers. all naturally occurring alpha amino acids are belongs to L form. We talked about L form and D form in our isomers part, right? We talked about it clearly. So except glycine, all other amino acids are optically active. This is the most important question you can expect from this amino acid part. Okay, so let's categorize these amino acids. The first category is amino acid with non-polar side chains. The simple ones like glycine. The structure of glycine is CH2, NH2, and another COO group is attached to it. That's why I'm saying this is optically inactive. And alanine, it's just a single variation, CH3, CH, NH2, COOH. This is alanine and this is glycine. Okay, so which are having non-polar side chains. And another example also valine, leucine, isoleucine. These are branched, but still they are not having any polar side chains. They are non-polar side chains. Special case in the first category is that proline. It is having a unique ring structure. It will be look like this. It doesn't fit in the general formula. That is also your additional point in case of proline. Okay. The second category is that polar but neutral side chains. In that case, hydroxyl containing side chains are serine and threonine. Sulfur containing side chains are cysteine and myothionine. Aromatic are tryptophan and triosine. This is important. And amide containing are asparagine and glutamine. Amino acids charged side chains. The charge can be of basic or acidic. Okay, the acidic side chains are aspartic acid and glutamic acid. And the basic side chains are lysine, arginine, and histidine. But the name indicates, you can remember it, they are acidic side chains, and these are lysine, arginine, and histidine are basic side chains. Okay, so while talking about the amino acids, the most important question is about zwitterions. Before that, you know about the amphoteric nature, which can act as a both acid and bases. This led to the formation of zwitterions, where the amino acids carries the both positive and negative charges. At a specific pH, that pH is called isoelectric point, the amino acid exists as neutral zwitterion, showing the minimum solubility. Next, our concept is types of proteins. We know that proteins are built up of peptide chains, and peptide chains are formed between amino acids. Amino acids are nothing but which are having COOH group and NH2 group. Okay, clear. So now we'll talk about proteins. Proteins can be classified into two: fibrous proteins and globular proteins. Fibrous proteins are have parallel polypeptide chains held together by hydrogen and disulfide bond, which making them insoluble in water, like keratin, which is in our hair, and myosin. In case of globular proteins, they form 3D spherical structures, typically soluble in water. Example, insulin, albumins. Important example. Okay, and protein structures can have 4 different levels: primary, secondary, tertiary, and quaternary. Among these 4, primary and secondary are super important. Don't worry guys, I'll link this doc with you. I'll put the link details in the description box. You can download it and make use of it. Let's see, primary structure. It is the most basic level, and you can see the structure over here. This is a covalent structure of a protein called primary structure, and it shows how the atoms in protein molecules are joined to one another through a covalent bonds. That is important. primary structures are linked through covalent bond. All proteins on hydrolysis give amino acids that we know. Particularly, these structure will give alpha amino acids. In case of secondary structure has, in case of secondary structure, this level show how protein chain begins to fold into regular patterns. The first part is that alpha helix. Alpha helix will look like this kind of spiral structure. Coil. Chain coils around itself like a spring. Okay, like a spiral structure. And in primary, we talked about covalent bonds, isn't it? Here, hydrogen bond is also taking place. Hydrogen bonds are between every fourth amino acid to stabilize this structure. This we can find it in keratin in hair, which makes it strong and flexible. Second structure, that is beta-pleated sheet, will be like this, like a sheet it will form, and this is here also the protein chain folds back and forth upon itself, creating a flat sheet structure. These sheets are particularly common in silk proteins, which gives us a unique strength. And these are having zigzag manner, and polypeptide chains are arranged side to side manner, as you can see, sidewise arrangement. The neighboring peptide chains are bonded together by intermolecular hydrogen bonds. Intermolecular hydrogen bond. Next, we are going to see tertiary structure. Here, the tertiary structure is more related to of 3D shape. The final 3D shape of a single protein chain, that is about the tertiary structure. The various forces are come into play. For example, hydrophobic interactions push some paths inward while the polar regions stay on the surface. This level gives the protein like a hemoglobin their specific functional state. You must have seen hemoglobin, right? It will be like this. So, tertiary structure gives the hemoglobin and myoglobin have this type of structures. Finally, quaternary structure of proteins. The complex proteins are formed from two or more alpha helix structures. Alpha helix structure, we already saw that it's just a spiral thing, right? In case of quaternary structure, this structure indicates the way in which these alpha helix structures of a complex protein are associated with each other. That's what the quaternary structure implies. Hemoglobin, once again, it has a 4 subunits, which is a classic example for this kind of quaternary structures. Tertiary and quaternary of the complex structures, they won't be asking much question except the interaction part. But primary and secondary structures, especially the secondary structure interaction part, what is the structure and what is an example for it, are most important. Okay, then we are moving on to enzymes and their properties. What are the enzymes? Enzymes are something related to catalyst kind of thing. Okay, so enzymes are the natural catalyst where we can see the enzymes. Enzymes are there in our body also. What it does is, when an enzyme meets a substrate, it forms a ES complex, enzyme substrate complex. This complex turned to be an intermediate 1 as a second step. Intermediate 1 then forms the product. Finally, the product breaks down and free enzyme and the product will be formed. Like very similar to our catalyst. What does it do? It facilitates the reaction. Right. Similarly, enzymes is also facilitates the reaction for the formation of product. Many enzymes are, most of the enzymes we can say with the name with ends with the A sound. Okay, maltase. We can see many enzymes name. Here also we have seen peptase, which used to break down our protein molecules. Right? Enzymes are needed in very, very small amount, and they are highly specific. That is, they catalyze a particular reaction only. Okay, they can't catalyze it everything. It's like a particular species, it's more selective one. And also it is very efficient. It can catalyze many millions of reactions per second. Specificity, it just follows the lock and key method. While we are saying about a lock and key, a particular key goes for particular lock, not for everything, right? Similarly, the enzyme behaves. It's suitable for the specific reactions or specific substrates to form product. It is a temperature sensitive, most work at the body temperature, around 37 degrees Celsius, and it is also a pH dependent. Around 7 pH it works. Okay, that's the important. Next, we are going to see a glance about vitamins. In case of vitamins, the most of the questions ask what are water-soluble vitamins, what are fat-soluble vitamins. These type of questions you should be taken care of. First of all, what are vitamins? Vitamins are the organic compound which can't be produced by the body. We are supplying it by our diet or medicines for the maintenance of our body. The multiple deficiency caused by the lack of more than one vitamins are common in human beings. This condition is known as vitaminosis, avitaminosis. And there are two types of vitamins. One is which are water soluble. Water soluble vitamins are B and C. BC. You can remember it like water is a busy business. So BC, B and C vitamins are water soluble. Other than this, A, D, E and K are fat soluble. Okay, one you remember, another thing will be easier. Okay, that's it about vitamins. They won't ask much questions. If they are asking also, they will cover in this part. Finally, we are going to see about nucleic acids and their hormones. First, nucleic acids are polynucleotides present in the nuclei of the living cells. We are made up of cells. Plants are made up of cells. Animals are made up of cells, isn't it? So these nucleic acids present in the nuclei. Nuclei, that is the center part of the cell, in the form of nucleoproteins. They are the fundamental molecules which is responsible for their heredity. Why we are getting our behavior from our parents? Knowingly or unknowingly, most of the behavior we are getting unknowingly from the parents. We are getting the features from our family, parents or grandparents. How we are getting it? It's because of these nucleic acids. Okay, so because of DNA, we are going to see more about DNA now. So nucleic acids are responsible for heredity and genetic information in all living organisms. First, pentose sugar. That is one of those essential components in nucleic acid. That is a 5-carbon sugar. The second thing, that is nitrogenase base. The nitrogenase base can be of two types. The one is pyrimidine base, the another one is purine base. We are going to see that. Okay, so first let's talk about purine bases. Purine bases are double ring structures. It has adenine and guanine. Adenine and guanine. Adenine contains 2 nitrogen rings and guanine contains 3 hydrogen bonds with cytosine. Okay. When this nitrogen bases and pentose sugar combines to form a nucleoside. Okay. So nucleoside, which is equal to pentose sugar plus nitrogenase base. Okay, that is nucleoside. Yes. Okay. What about nucleotide? In case of nucleotide, it is made up of nucleoside plus phosphoric acid or another pentose sugar. Phosphoric acid or pentose sugar plus a nitrogenous base and then again phosphoric acid. So that is about nucleotide. So talking about nitrogenous base, I told you there are two categories, pyrimidine base and purine base. Purine bases which has adenine and guanine. Similarly, pyrimidines are having cytosine, thymine and uracil. You have to memorize this. You can remember like pyrimidines cut, cytosine, uracil and thymine. And this is AG. Aged cut. Can remember it like that. Okay. So in that case, the uracil, U, it's only present in RNA. Rest of the things are present in DNA, but in case of uracil, that is present in RNA only. Okay. Then, what is the difference between RNA and DNA? These are the general differences. Most important point is what is the pyrimidine base and what is the purine bases present in DNA and RNA. First, DNA means 2-deoxy-D-ribose. The name, of course, that is important. RNA is D-ribose. Pyrimidine bases present in DNA, cytosine and thymine. In case of RNA, uracil and cytosine. Purine bases present, adenine, guanine. In RNA also, adenine, guanine. Structure, in case of DNA, that is double-stranded helix. Like you have seen the structure like this. You can see the structure like this. For double-stranded helix in case of DNA. And RNA, that is so simple, single-stranded structure. Location is DNA present as the main nucleus and RNA present in nucleus plus cytoplasm. Replication, it is self-replicating, and RNA, that is not self-replicating. Size, DNA size is larger, but in case of RNA, that is smaller. Stability, more stable, but RNA is less stable. Out of this, the first 4 points are very, very important. Okay. Then, another type of question can be asked from here, that is from this rule. Chargaff's rule. It either can be NEET or mains, advanced, any other examinations. This is important. The first rule is amount of A, adenine, which is equal to thymine, and guanine, which is equal to cytosine. That is first rule. A equal to T, G equal to C in case of DNA. Second rule is purine bases, which is equal to pyrimidine bases. Okay. Next thing you have to remember how it is getting paired. A, that is having 2 hydrogen bonds in it. A and T. T is having 2 hydrogen bonds. G and C, guanine and cytosine, which is having 3 hydrogen bonds in it. In case of RNA, thymine is not there, so uracil comes. Okay, A is equal to U. So we'll see the questions in a while. You have to remember this adject. Adject, you have to remember this. Okay. Then, what are the biological functions it is doing? First, as I said, replications, DNA copies it is producing, and then protein synthesis, transcription. Transcription is DNA to RNA. Translation is something like RNA to protein. Translation, the mRNA directs the protein synthesis by this process. That is called translation. Transcription, that is the process of synthesis of RNA and DNA in the cytoplasm of the cell. Genetic code, the linear sequences. A means next to that, T should be there. That kind of sequence is also that biological functions significance. Then, mutations. What happens in mutations is that the change in nitrogenase base sequence of our DNA molecule which lead to the synthesis of the proteins with an alternate sequence of amino acids. You must have heard this term, mutations, in coronavirus period. Second variant, third variant. Because of this changes of nitrogenase base. These changes of the sequence basically, which is responsible for the protein structures change. The altered amino acid sequence has been formed. Okay, this causes the genetic disorders. Okay, let's see some problems related to this nucleic acid because that is most important concept of this chapter. Calculate the number of hydrogen bonds in DNA segment containing 30% of adenine. Total number of nucleotides they have given, that is 100. Okay, so we know that